So good morning, everyone, and thanks again for the invitation. Thanks also to the organizers for setting this up. It's a pleasure to be here, and well, I hope you will enjoy the presentation. Before I do anything else, I should encourage you again to ask questions, as Monica did, so do feel free to interrupt at any time. I have, in principle, timed this so that it lasts, well, actually, there's a basic course which is about 2 hours, even a bit less. If you ask questions, it's going to be longer, but I'm very happy to make it longer as long as people are interested. So, feel free to interrupt, we can discuss. And so, yes, as announced, this is going to be a mini class, I guess, on what I'm calling baby BMS, which really means Bondi-Meitner-Sachs symmetry in 2+1 space-time dimensions. Normally, BMS symmetry is defined in 3+1 dimensions, which is sort of the real world. This is gravity in 2+1 dimensions, which has no local degrees of freedom. So this is a baby version of the problem, but I'm going to argue that it already contains lots of interesting information about the problem. So I'm going to start with a general motivation for the problem. The motivation comes from the desire to quantize gravity. We don't really know how to do this. And there are various ways in which you can try to address this question, but one very conservative way is to say, well, gravity is a gauge theory, so let's ask more generally what we can say about the quantization of gauge theories. And so in that context, one specific aspect of quantization I'm going to talk about today are called asymptotic symmetries. So without going into the details, asymptotic symmetries in any gauge theory are gauge transformations that do not fall off to the identity at large distances. And they do this in a very specific, constrained way, such that they have non-zero Noether-like charges, but they call them Noether-like because they're actually not, well, they're surface charges. And when I say surface charges, well, let me explain what I mean by that. Oh, yes, by the way, if anyone doesn't see something also online, if you don't hear me online or anything, please just let us know as soon as possible. And so in particular, I'm actually going to use the far sides of the blackboards to keep certain drawings and equations that I'm going to refer to. So if you don't see them, please let me know. So one drawing I'm actually going to use now is the following. So I said that these asymptotic symmetries have Noether-like surface charges associated with them. So what I mean is that when you have a space-time, such as this one, what you normally call a Noether charge is a charge obtained by taking a space-like hypersurface and integrating some current over that surface. But when I talk about surface charges, and those are actually the charges that exist in gauge theories, surface charges are instead integrals over surfaces of codimension 2. And so this is where you're going to integrate whatever object you have to integrate so that you get a surface charge in a gauge theory. And so in particular, you can really tell just by staring at this drawing, there's sort of a holographic flavor to the whole story. And this is true for any gauge theory. In any gauge theory, you're going to have this notion of integrating something over a codimension 2 surface instead of a codimension 1 surface so as to get a conserved charge. And so this is crucial because, for example, in the quantum theory of your gauge theory, including in quantum gravity, these surface charges are going to span a symmetry algebra. And this symmetry algebra is typically represented unitarily in the Hilbert space. And so whatever Hilbert space you have, you can now organize it into irreducible unitary representations of the symmetry algebra. And then you can use this as a sort of organizing principle to get some information on the Hilbert space. For example, in CFT, you would use representations of Virasoro to do this. Well, in BMS, you can try to do the same. So this is the broad motivation for what I'm talking about. Now, specifically, asymptotic symmetries in the context of gravity have actually long been known to play a role. So here I'm going to summarize these very famous applications. I'm not going to follow a historic route. Instead, I'm going to follow one that's sort of logical given the course I'm going to give. So the first application I want to talk about is the computation by Brown and NO, who back in the 80s studied ADS3, so asymptotically ADS3 gravity, anti-de Sitter, by the way. ADS means anti-de Sitter. And they found, so when I say ADS3, I mean 3 space-time dimensions. So it's really anti-de Sitter gravity without local degrees of freedom. And they found that the asymptotic symmetries span the conformal group of the boundary, which from a modern perspective is completely natural, because this is really just a sort of, well, you know, it's a precursor of what we call today ADS-CFT. But crucially, they found that this conformal group acting on the boundary has non-zero central charges, called the Brown-Renaud central charge. And this is really a topic to which we're going to return in the course, because we're actually going to use this as a sort of guide into how we're going to do this for BMS in 3D. Then the second application I want to talk about is actually one that came long before Brown-Renaud, and that's actually the one that gives its name to this class. So Bondi, Vanderburg, Metzer, and Sachs, back in the 60s, so what they studied was asymptotically Minkowskian gravity, or asymptotically flat gravity, in 3+1 in 4D. And specifically, they looked at the asymptotic symmetries of this system at future null infinity. So let me just make a drawing to explain what I mean by future null infinity for those of you who may not be familiar with the concept. So here is a Penrose diagram of Minkowski space. Actually, here I'm drawing it in 2+1 dimensions, which is going to be exactly appropriate here. And so the region on which they looked, well, on which they focused, is here. This is future null infinity. It's null, of course, because, well, it literally goes in a null light-like direction. So on this region here, they built certain conserved charges, and they found a symmetry which to them was a surprise, because what they were actually expecting back in the day was that they would find, so do I have space here? Yes. So what they were expecting was to find Poincaré, which, as you know, is a semi-direct product between Lorentz and translations. But to their surprise, what they found was a much larger group, which ended up being called the BMS group, which is a semi-direct product of Lorentz with an infinite dimensional group of what are called now super translations. And these super translations provide an infinite dimensional abelian extension of the usual group of space-time translations. I should mention that the prefix super here has nothing to do with supersymmetry. It simply emphasizes the fact that this is infinite dimensional. And so actually back in the day, BMS thought that this was a problem. They thought of this as a pathology. But from a much more modern perspective, yes, so let me do this. From a much more modern perspective, including ADS-CFT actually, it's sort of a good thing to have infinite dimensional symmetries, because it means you can very heavily constrain your system. And in fact, in 2010, Barnish and Troussard went much further in trying to extend this in an infinite dimensional way. So I'm actually going to write here what they did. So what Barnish and Troussard suggested in 2010 was to revisit the BMS analysis and actually extend this even further. So BMS, I don't know, extended, to extend it in such a way that you still have super translations as before, but actually you extend the Lorentz group into what Barnish and Troussard called super rotations. Now, I will not go into the details times super translations. This doesn't change. Now, I will not go into details here of what super rotations are in 4 space-time dimensions, but essentially they're local conformal transformations, arbitrary, non-invertible local conformal transformations of celestial spheres, meaning that if you're an observer located somewhere here in Minkowski space, you can, the region that you sort of see around yourself is a sphere. Here it's going to be a circle, and that's called a celestial sphere or a celestial circle in this case. And in particular, the subject that Andrea talked about some weeks ago was celestial CFT, which is the proposal to actually try to define a CFT on those celestial spheres or in 2+1 dimension celestial circles. And so, in fact, as Andrea argued as well, today asymptotic symmetries are pretty much at the forefront of research on, well, quantum gravity in particular, but even gauge theories in general. And in particular, there's a bunch of really pressing issues that need to be addressed regarding BMS symmetry. Now, I actually want to write those issues as a sort of checklist, because I'm going to argue that baby BMS gives you a handle on some of them. So I'm going to do this on this blackboard here on the far right, because that's something I can keep for later. So pressing issues. This is still the introduction, by the way. I still haven't actually started talking about I'm still in section 0. Any questions at this stage? Okay. So some pressing issues with BMS. Well, the first issue is that so superrotations in 4D, so these local conformal transformations of celestial spheres, are singular. In particular, they're singular in the sense that they're literally not invertible diffeomorphisms. So they're not diffeomorphisms of a sphere. They create singularities, and in particular, they tend to create, I guess, probably infinite energy. And so that's a problem. No one really knows how to regularize this. So that's, I guess, a puzzle. Another puzzle that is perhaps a bit less well known, but it's sort of tied to this, is that there exists in BMS a dimensionful central charge between superrotations and supertranslations. And well, the interpretation of this central charge, its physical consequences, its application to the computation stable black hole entropy are completely unknown at this stage. And so this is a second issue that I think is currently very much at the forefront of research. Monica, you seem to have a question.
4 dimensions?
Sorry?
This is in 4 dimensions?
For now, this is all in 4D. So I'm still for now in this setup, in the setup of 4 space-time dimensions. But I'm soon going to argue that actually BMS in 3 dimensions, which I'm soon going to introduce, is going to highlight some aspects of answers to all those questions I'm currently writing.
Okay, can you just scribble what the central charge looks like in this case?
I can scribble it.
If it takes too much time, then never mind.
So it's complicated because it's actually well, it's a state-dependent central charge. It's a central charge that depends on the asymptotic shear. So do you know what the asymptotic shear is in 3 + 1 dimensions? It's a function CAB or CZZ. So that function actually is the central charge, but it's a function. And so in particular, depending on whether you're in Minkowski or in a Kerr black hole or in a radiative space-time, you're going to have different values for the central charge, which is completely not what happens in 2 + 1 dimensions. So in that sense, I prefer to be vague here because if I were actually specific, you would very quickly see the huge differences that there are between BMS in 4D and BMS in 3D. While here, I'm advocating that the two are sort of similar. So I'm sort of hiding this subtlety under the rug. So it's a crucial subtlety, but already the sole fact that you have a dimension-full central charge, which is not a Virasoro central charge, it's not exotic from a mathematical perspective, but from a physical perspective, it begs for some sort of explanation, for some sort of physics that we explain it. And this is what baby BMS is going to do. And so, yeah, I can scribble it later if you're interested. There's a question, Monica, behind you.
Thank you.
And another one here.
What sets the dimension of the central charge?
Sorry?
What sets the dimension of the central charge?
What's the dimension? What do you mean by dimension?
I mean, if you say the central charge is dimension full, right?
Yes, yes. I just mean that it's, so in a Virasoro algebra, the central charge is a number, 1, 2, whatever. Here it's, well, in BMS, in baby BMS, you'll see that it's actually the Planck mass. Well, of course, the problem with dimension-full central charges is that they're dimension-full, which means that if you choose suitable coordinates, you can set them to whatever value that you like, which in fact is part of the puzzle. The puzzle is, you know, if you're used to CFT and Virasoro representations, you know that the actual value of the central charge strongly affects the physics, like you have minimal models versus non-minimal and so on. So when you have a dimension-full central charge, it feels like it's so completely arbitrary that you can actually set it to 0. Well, crucially, you cannot set it to 0, but the actual value again is just a matter of conventions. In standard units, standard in the sense of the literature, it's actually the Planck mass. Yes?
I want maybe state that a little more simply. So in ADS3, we know that we have 2 scales. We have the ADS curvature and we have the Planck mass. So we can make a dimensionless parameter out of this, which is the central charge, the Brown-Henno central charge, right?
Okay, yes.
It's LADS over G Newton.
Yes.
But in the flat case, we only have G Newton. So
exactly.
Only we can make some dimensionful
parameter.
So
right? Indeed, from the perspective of dimensional analysis, this is a very good way to see why things, but you'll see all this later in the course. But so again, this is the intro. But indeed, from dimensional analysis, it's sort of clear that in flat space, you cannot build a dimensionless central charge. Thanks. Thanks for the questions.
Can I follow up a little bit?
Yes.
Sorry, I just want your your point of view on that in the big picture. Why do we call it a CFT if that's true?
Why do we call what a CFT?
Whatever the celestial CFT on the boundary that
I don't
we're
call it a
studying is.
CFT.
Okay, thank you.
I don't call it a CFT. I actually, well, I prefer not to call it a CFT because thinking of it in terms of CFT is going to be, at least, I can essentially prove in 2 + 1 dimensions that thinking of it in terms of a CFT is not going to give you the right picture, because super translations really are, the abelian part is actually, in a sense, more important than the super rotations. So, but we'll get there. So no, I'm not calling it a CFT. I am saying, though, that there is a notion of, I mean, there's for sure a notion of conformal structure on this celestial sphere or celestial circle. And of course, studying that conformal structure gives you important physical insight, that's for sure. Good, thanks. So the pressing issues with BMS, first, those are completely classical. They are singular 4D superrotations, and there's a central charge classically between superrotations and supertranslations, although it's very complicated. On the quantum level, actually, the unitary representations of the BMS group are, well, they're technically known in the sense of this old-fashioned BMS group that was done by McCarthy in the 70s. But I think there are very strong arguments to say that this is actually very incomplete and that there's a missing understanding, in particular in relation to, well, the relation between BMS and soft theorems. And so this is completely not understood at present. In particular, these unitary representations should somehow be related to what Kulish and Fadeev called dress states. And this relation at the current stage is completely obscure. No one knows this. No one knows how to establish this relation. And finally, from a sort of ADS-CFT perspective, you would be tempted to try to do some sort of holography for flat space gravity. And again, in 3 + 1 dimensions, this is sort of just barely starting to be done now, but in 2 + 1 dimensions, you can actually say quite a lot. Andrea, you have a question.
Yeah, just wanted on the last point that you made before the holography part. What you meant that the relation of dress state and BMS is not
right. So you would want a dressed state in the sense of Kulish and Fadeev to be an irreducible unitary representation of a suitable asymptotic symmetry group. If you take your asymptotic symmetry group to be this guy, Lorentz times super translations, that's not true. The irreducible unitary representations of this guy are just usual relativistic particles without any dressing. There's no notion of dressing here. There's actually essentially no notion of soft gravitons here, even though the word identity for super translations is the soft theorem of Weinberg. But actually, if you look at the Hilbert space that you build based on this, you don't get soft gravitons. So some extension is necessary to get soft gravitons. And one suggestion would be to take superrotations and see where that gets you. But maybe there are other proposals.
But there's also proposals to extend the phase space by adding the soft gravitons. And there is an understanding of what, there's at least a subset of the Fadeev-Kulish states which come out very naturally when you think about the full, the extended BMS.
Yes.
And
no. So this guy, BMS, for example, or even this if you want, does act unitarily on Fadeev-Kulish dress states, but not in an irreducible way. So in other words, if you take the Hilbert space of a particle dressed with soft gravitons, you can foliate it into UE reps of BMS, or even of extended BMS in this sense. And that's fine, of course. It has to be that way. But from the perspective of particle physics, it's sort of frustrating because the whole point of Wigner's classification, I guess almost now 100 years ago, was that he looked at irreducible representations. So irreducibility is an issue. So thanks. It's a very good question, and yeah, we can talk about it more. So what I'm going to argue is that these issues are pressing issues for BMS in 4D, but actually baby BMS, i.e. BMS in 3 dimensions, is actually going to partly address all of those issues. So I'm going to have, I'm going to put checks here every time I actually tell you how we've addressed one of those points. And so with this motivation in mind, here's finally the plan. So plan. And there's just going to be essentially two sections. The first section is going to be a definition of the BMS3 algebra. And I stress from now on that it's going to be BMS3. In particular, I'm going to show that BMS3 is an ultra-relativistic Carolean limit of the Virasoro algebra. And I'm going to relate this definition to, well, what I'm calling, in short, boundary gravitons. But those are really boundary degrees of freedom of the gravitational field in 2 + 1 dimensions. And then the second step is going to be, so this is pretty classical. The second step is going to be quantum, because I'm going to talk about unitary representations. And I'm going to argue that you can think of them as particles in the usual sense, so asymptotic states of, asymptotic scattering states in QFT, which are dressed with quantized boundary gravitons. And so in a sense, this last point provides you with at least a starting point of handle to the first question I asked, which was how to actually quantize, at least perturbatively here, gravity. So that's the broad motivation. And I guess I can actually start now with section 1. So just to see how I'm doing with time. Sorry? Indeed, I do. That's a good point. Yes, very good. Actually, it's okay. It's a bit longer. One page is supposed to be 10 minutes. Okay, fine. So I want to define. So first section, big section. I want to defining BMS. By the way, so from now on, to save some syllables, when I say BMS, I always mean BMS in 3D. I always mean baby BMS. So I just say BMS for brevity. And so here I want to do the following. First, I'm not going to review the whole construction of asymptotic symmetries and surface charges. I'm going to take sort of a shortcut. And the shortcut is going to be to write just Poincaré in boundary coordinates and argue that there's a natural extension, so boundary coordinates in 3D, and then argue that there's a natural generalization to get BMS. But then, so that's fine, but it's still not convincing enough. So I'm actually going to take an ultra-relativistic limit, so UR limit of ADS3 CFT2. And by taking this limit, we'll find that we actually find the BMS algebra with now non-zero central charges, which is what's actually realized as surface charges in gravity. And finally, I will actually talk about boundary gravitons. So when I say boundary gravitons, from this perspective, they're really going to be currents associated with BMS transformations, currents dual to BMS transformations. And this will in particular lead to an interesting classification of asymptotically flat matrix. This is all at this stage completely classical. In particular, the word graviton is sort of a misnomer, really, but it's standard in the literature, so I'm going to keep using it. So these pictures I want to keep, but this is fine. This I can just remove. Yes, sure, go ahead. I'm listening. I just want to save time by erasing while listening to the question. So please go ahead.
So how recent is the story with BMS3, like this baby BMS?
Well, it depends which aspect of the story. There is a very, relatively old paper by Ashtekar, Bichak, and Schmidt, which was the first, I think, to introduce BMS3, although not with that name. And that paper dates back to either the 80s or the 90s, I'm not sure.
I see.
But then that was sort of not really studied much for a long time, as far as I know, at least. And then, to my knowledge, so if someone knows better, please correct me. But so, I come from Brussels, so I'm biased by the Barnish school. But to my knowledge, around 2010, Barnish had Cédric Troussard as a PhD student, and together they suggested this idea of superrotation. They said, well, this was also hinted at by Tom Banks independently, but really, Barnish and Troussel worked on it in quite some detail. And so that's the point. Actually, that's the point when Glenn realized that there were huge issues with BMS4, including superrotations. And then he thought, well, what can we do to make it simpler? And he looked at 2+1 dimensions and realized that there was actually a central charge. So actually, I think he did this before Cedric. He did this with Jeffrey Compare. So he found a central charge with Jeffrey Compare. And then, well, my thesis was about essentially, I guess, these two aspects. And then, well, these two aspects plus representations, plus characters, plus all the quantum aspects. Okay. But so, I mean, what I'm going to talk about here is really relatively recent, in fact.
Okay.
Although, as you will see, it's sort of basic. You don't need incredibly elaborate tools to address those points. So that's the plan which I'm going to keep for now. Okay, good. So point A, BMS extends Poincaré. So as I said, it's going to be completely elementary in the sense that I just want to consider Minkowski space, so 3D Minkowski, with the metric which is, well, the one you know, in inertial coordinates. Fine. So what's a Poincaré vector field? Well, so a Poincaré vector field is a generator of isometries of Minkowski, so you can write it as, do I have enough space here? I'll write it here. So it's Xi, which is some translation, A mu d mu, plus omega mu nu x nu d mu. So this is a generator of translations. This is a generator of Lorentz boosts and rotations. And so omega and A are just constant parameters. In particular, A naught is a time translation. AI are spatial translations. Omega 1, 2 is a rotation. Omega 0, I are boosts. Fine. OK, so now suppose that you want to hurt yourself and write this in retarded Bondi coordinates. So by this, I mean that when we declare that x1 is actually r cos phi, x2 is r sine phi, so these are just usual, I guess, cylindrical coordinates, and we declare that x naught, I guess, is u plus r. So in terms of this Penrose diagram here of Minkowski space, you should think of this as saying that the coordinate u runs here, so it's sort of a null time coordinate on future non-infinity. The radial coordinate here tells you how far you are from an arbitrarily chosen origin in space-time. And the angle phi labels points on celestial circles. And so, yes, the word celestial circle is something I'm going to use throughout. And so suppose that you use these coordinates now, and you rewrite this vector field in those coordinates, because you want to. So exercise, this is something you can do with what I gave you. At large r, so as r goes to infinity, I'm going to neglect subleading corrections which are not crucial. But at large r, what you find is that actually this guy is asymptotic to alpha. So I'm going to write it and then explain what I'm writing. So first, let me write it. So it's alpha plus u epsilon prime du plus epsilon d phi minus r epsilon prime dr. So here, what I'm calling alpha and epsilon are two functions, where alpha of phi, by definition, is a naught minus a1 cos phi minus a2 sine. And what I'm calling epsilon is, by definition, again, minus omega 1, 2 minus omega naught 1 sine phi. No, sorry, yes, minus omega naught 2 cos phi. So you have just rewritten an exact Poincaré vector field in Bondi coordinates asymptotically. I'm neglecting here subleading corrections. And so that's it. Now you're essentially done, because now you can generalize. You can take an asymptotically Minkowskian metric. And again, I am not going to be precise about what I mean by asymptotically Minkowskian, but sorry. There's one thing I didn't say, of course. The metric here, you can, of course, write it in Bondi coordinates, and the form it takes, so this is at this stage exactly Minkowski. it's minus du squared minus 2 du dr plus r squared d phi squared. So that's the Minkowski metric written in boundary coordinates. Now, the generalization I'm talking about is one where you declare that you're going to do general relativity, and you're going to impose that the family of metrics at which you actually look are not exactly Minkowski, otherwise there would be no gravity, but instead are asymptotic to this kind of expression at large R, plus some corrections, which I don't bother writing down those corrections for now because they're not going to be crucial. But later on, I will actually write you down the on-shell version of this metric. But at this stage, this is an on-shell, sorry, this is an off-shell requirement. You just say, I consider the phase space of 2 plus 1 dimensional gravity, where all my metrics take this form up to certain specific prescribed corrections, which you can find in the literature, but which I don't want to write down here. And so then you can ask, what are the vector fields that preserve those fallouts that I haven't written, but you can actually ask the question. And so if you do this, what you find, so what vector fields preserve Minkowskian fallouts? Well, the answer is all vector fields of this form, except that your functions alpha and epsilon now are completely arbitrary. So this is an infinite dimensional extension of the Poincaré symmetry. Poincaré was 6-dimensional because you have 3 translations and 3 Lorentz. Here you have infinitely many abelian transformations alpha and infinitely many reparametrizations of the circle generated by epsilon. And so now terminology, epsilon, I'm going to call a super, well, actually I'm going to call it a super boost instead of a super rotation. So I should mention that the word super rotation is more standard, but super boost has fewer syllables, so it's much more convenient. And also it's actually much more correct in terms of homotopy groups. In terms of topology, super boost gives you the right picture, while super rotation sort of implies that there's a notion of non-trivial first homotopy, which is incorrect. So super boosts are actually a more correct name, I think, which I'm going to use. And so these really just extend Lorentz vector fields, as you can see. And so, and alpha, I'm going to call super translations, as is by now standard. I stress that at this point, I haven't actually, I've just taken Poincaré, written it in boundary coordinates, and then used sort of an educated guess to say how this should be extended. I haven't really done the computation. So later on, I'm going to take an ultra-relativistic limit of ADS-CFT to argue that this is really what you should do. But at this stage, you should just, take this as a good motivation. And so, yes?
Just regarding the motivation, so sometimes people use as motivation just the fall-off of non-solutions. I guess here you'd be having some sort of conical defects that would presumably have the fall-off that you've included. Is there anything else that people consider in BMS3?
So you can derive BMS3 with the same arguments with which Brown and Eno derived the conformal group in ADS3. And there were 2 key points to this argument. One key point was that the phase space has to include ADS3 and conical deficits, as you said. And the second point was the group has to include the isometry group of ADS3, which is non-trivial because, as you know, there's, for example, this Comper-Sung-Strominger symmetry, which probably there's a warped ADS3 symmetry as well, which doesn't actually include SL2 times SL2, right? So Brown and O emphatically had 2 assumptions. They wanted to have SL2 times SL2, and they wanted to have conical deficits. And if you do this, you get their conformal group. Here you can do the same thing. You can require to have the smallest possible group that contains all conical deficits and contains Poincaré, and you would get this. So yes, you can run that argument.
But you don't have obviously you don't have anything like gravity waves or anything like that.
No. So the phase space that so at this point I'm not talking about the phase space. This is purely kinematical. But there are no local degrees of freedom in 2 plus 1 gravity. So of course you have no gravitational waves, and so all the time-dependent subtleties that occur in 3 plus 1 dimensions do not occur here. And so, fine. Thanks for the question. So definition, the BMS algebra, BMS3 being understood, is the set of pairs epsilon alpha with the bracket which you can deduce from the expression of the vector field I wrote here. So if you take one such vector field and asymptotically compute the Lie bracket, what you're going to find is that the bracket of psi of epsilon alpha with psi of, I guess, zeta beta is actually psi of epsilon zeta. And then here you have epsilon beta minus zeta alpha. Where, so this is the Lie bracket of vector fields in space-time. What I'm writing here, this by definition is epsilon zeta prime minus zeta epsilon prime, and similarly for those guys here. And so abstractly, the BMS algebra is an algebra of vector fields on the circle, which are those epsilons, which are super rotations, super boosts, taken in a semi-direct sum with, now, it's a semi-direct sum with super translations, so technically I could write here the abelian group of functions on S1. But actually, I'm going to, if I write this, I have to tell you how these vector fields act on these functions. So instead of doing this, I'm going to use the fact that vector fields act on functions as if those functions were vector fields, even though the functions themselves commute. So I'm going to write this as vect S1 abelian. Yes. I hope this notation is not confusing, but it's actually quite important that this is the vect S1. So this is vector fields on the circle, which act as reparametrizations of the circle, which are superboosts, which act on super translations, which are just functions on the circle, but they transform under superboosts as if they were vector fields. Is that clear? Okay, I see people nodding, so hopefully it's clear.
I guess it's clear. Is it also just for even more clarity, is it possible to write this in terms of Fourier modes of alpha and epsilon?
Yeah, I'm getting there.
Okay, good.
I'm getting there. I know that people like Fourier modes, so yes, I'm getting there. So just before Fourier modes, there's just one, well, I could start with Fourier modes, actually. Okay, yes, let me start with Fourier modes. So as Monica was asking, let me write this in terms of Fourier modes as you would normally do in CFT. So you introduce a basis of this algebra, which you call, so you have two families of generators. You have the non-abelian ones, the superboost generators Jm, which are just psi associated with epsilon, which is e to the im phi, where m is an integer and alpha is 0. And you have a family of super translation generators, which you call Pm, which are psi's of epsilon, which is 0, and alpha, which is e to the im phi. And so if you now compute this bracket, these brackets for those guys here, what you find is that I, Jm, Jn equals m minus n, Jm plus n. I, Jm, Pn equals m minus n, Pm plus n, and I, Pm, Pn equals 0. Okay, and so several comments. The first line is just the Witt algebra, which you're going to extend to Virasoro eventually. The second line takes exactly the same form with the same structure constants, which is the statement that super translations are actually vector fields in disguise. That's why I'm saying that they're vector fields, because the bracket is really the same. And super translations are, of course, abelian. In particular, the Poincaré algebra is the subalgebra of this, for which the indices mn takes values -1, 0, 1. Okay? Good. So we've extended Poincaré. One last thing before I actually move on to the next subsection. Good. So one last thing is that, so the BMS group acts on null infinity. Well, these are, I wrote BMS vector fields there. And so you can actually exponentiate those vector fields to see how they act on some points with coordinates phi and u on null infinity. And what you find is that this is mapped in general on any diffeomorphism f of phi. And the u coordinate happens to be mapped on f prime of phi times u plus alpha of f of phi. And so again, the interpretation is sort of clear. This f is now a finite, not infinitesimal super rotation, a super boost. So it's really a diffeomorphism of a circle. This u coordinate is time, and it's multiplied by the derivative of this guy. So this sort of measures if you have stretched the circle at some point. And then it's translated in an angle-dependent manner by the super translation. So this is really the usual action of actually BMS even in higher dimensions. And I should mention, and this is actually something I'm going to keep until the end of the talk, that from this action, you can deduce. So here I wrote the BMS algebra. Now let me write the corresponding group. So the BMS group, which is the group of all these transformations, is actually a semi-direct product between the group of diffeomorphisms of the circle and the vector space of vector fields on the circle seen as an abelian vector group. So this is the proper definition of BMS in 3D without any central extensions at this stage. So any questions at this point? Okay, good. If there are no questions, then let me proceed. Again, do feel free to ask. So I put this equation here in a box because I'm actually going to use it later also for representation. So that's why it's sort of good that it's almost on the far right. I can keep it there. Good. Now let me actually erase what I do not need because I'm going to move on to the next subsection. At what point do we make a break? Okay. Sorry, what? Yeah, sure. No, this, of course. Which one do I want to keep? I guess, well, yeah, I really want to keep this, and I really want to keep this, but I'm keeping it, okay, keeping it in the wrong place. I'm going to keep, and the metric I'm going to rewrite here. So this I've already written. I'm just rewriting it for later because I'm going to use this at some point. The chalks are really good, by the way. They're nice. I mean, even when it's wet, they can still write properly, and it's a pleasure to write with them. So cool. This is it's actually non-trivial. So this I have this I've said all of it. This I can just erase.
I have a question about this this algebra you just wrote down.
Sure, go ahead. So before I'm going to erase while you speak.
So in conformal field theory, we have these L's and L bars, and there is this L dagger related to L dagger of n related to L minus n and all. Yes. So what's the analogous statement here?
Sorry? What's the analogous statement here? Okay. So, well, it's actually sort of the same. Okay, yes, indeed, I'm already erasing what you're asking about. Well, okay. Yes, these are real vector fields. There's no notion of complexification here, right? So you have to map phi on, well, a real diffeomorphism of phi. So when you actually take a vector field on a circle and expand it in terms of those Fourier modes, you would write it as some combination of coefficient Cm times Jm. But because this is real, you have a constraint that Cm star, the complex conjugate, is actually C minus m. So you're going to find, so when you move on to the quantum theory and look at unitary representations, you're going to have the same Hermitian conjugation rules as you have in CFT. So literally, generator M dagger equals generator minus M. So this we will have eventually. When I talk about representations, you will see this. And also you will see it in terms of currents. Currents will have to be real, which means that in the quantum theory, they're Hermitian operators, which means that when you expand them in Fourier modes, you have to have Lm dagger equals L minus M. So definition BMS, this I've said. With the bracket I've written. That's fine. Abstractive BMS, okay, this is all done. Okay, and let me keep the Fourier modes here for now, though I think I can actually erase them, but fine. Okay. Yeah, so as I was preparing this, I realized I was keeping a lot of pictures and equations like for a long time, and I was worried at some point that I wouldn't have enough space, and this is starting to show, because you see I'm starting to spread over the blackboard here. So I hope I will have more than just one little line to actually write my ongoing discussion, but okay, let's hope it works out. So now I want to, so this is subsection B of section 1. BMS as a limit of Virasoro. So I have for now presented BMS as something that extends Poincaré. Now let me take a completely different, well, ultimately the same point of view, but in fact naively different, which is to say that instead of looking at asymptotically flat gravity, we're going to look at asymptotically anti-de Sitter gravity in 3D. So ADS3 gravity, asymptotically ADS3 with a cosmological constant lambda, which is -1 over L squared. Well, L is the ADS radius. And so we're going to try to take a limit of what you normally do in ADS3 CFT2 and see if we recover BMS from that. So in particular, you can think of ADS3 as really this cylinder here, where now I'm going to have coordinates here, a time coordinate which I'm going to call U, a radial coordinate which is going to be actually a Bondi coordinate R, which goes here, and then again the angle phi goes here. So that's really the picture I want you to keep in mind. But instead of describing things in terms of U and phi, it turns out to be more convenient to describe everything in terms of light cone coordinates on the boundary. So these light cone coordinates I'm going to call them x plus or minus, and they are by definition U over the ADS radius plus or minus phi. In particular, notice already from this that you can think of 1 over L as the speed of light on the boundary. If you think of this as a light cone coordinate, well, this is then like x plus c plus or minus ct. So c is 1 over L. And so when we take the limit where L goes to infinity, that's 1 over L going to 0, so c goes to 0, so that's a Carolean limit. So we're going to be interested in the Carolean limit of this. Now, what are the asymptotic symmetries here? So this is not something I'm going to derive. I'm going to rely here on, well, your intuition and some knowledge of ADS-CFT. So asymptotic symmetries are actually conformal transformations which map, say, x plus on any function g of x plus, and, colors. I knew I needed colors at some point. And x minus on some other function g bar of x minus. Good. And so the generator for these transformations is actually a vector field xi, which asymptotically in space-time takes the form of some function epsilon of x plus, d plus some other function epsilon bar of x minus, d minus. By the way, notice that this, so this in LaTeX, this would be backslash epsilon, while this would be backslash var epsilon. I'm using two different epsilons, and this is going to be important. Good. It's nice that we all speak LaTeX. Sorry? I could, yes, but I like to avoid, I mean, if I can avoid as many Greek letters as I can, or well, any letters at all. Anyway. So, okay, fine. So again, just a lightning review of ADS-CFT. The surface charge associated with a conformal generator is actually a CFT Noether charge on the boundary. And that CFT Noether charge takes the form of Q epsilon epsilon bar equals integral d phi over 2 pi epsilon t of x plus epsilon bar of x minus t bar of x minus, where t and t bar are the components of the stress tensor of the CFT on the boundary. And then finally, so here actually I think I want to keep some space, so I will. And then the Virasoro generators are just the Fourier modes of the stress tensor, which I don't need to write down, and they satisfy the Virasoro algebra, which takes the form. So I'm going to, here, I want to be sort of completely classical, so I'm going to write an algebra of Poisson brackets, which is why you're going to see I times the bracket. If you quantize this, that just becomes the bracket of, well, the commutator of operators. But here I'm classical, so let me write it as I times Ln equals m minus n Lm plus n plus c over 12 m cubed delta m plus n, 0. And then you have the same algebra for bars, except there's bar, and then there's another central charge here. And what Brown and Eno famously showed was that actually the central charge C is essentially the ADS radius over Newton's constant. But in fact, to be more general, I should say that sometimes, well, sometimes in parity breaking theories, actually no, in parity breaking theories, there's actually an extra term here, which I'm calling A because it's, well, do I want, yeah, I guess I can call it an anomaly if you will, so I'm calling it A, but it emphatically doesn't depend on L, and I want to keep it because when I take the limit, you will see that it actually plays a role. But really, the main point is you can forget about this, and really, C and C bar are essentially 3L over 2G. That's the Brown-Deneau central charge. Monica has a question, yes.
And to get this A, you basically need to couple this to TMG.
For example, TMG, yes. I presume there are other examples, but TMG is the prototypical example where you get it, yes. Yeah, so it has to be parity breaking in some way. If it's, I guess you can just take two Chern-Simonses with different levels and you would get the same thing as well, right?
Right, but I guess those would be equivalent.
Yes.
Is precisely what's capturing.
Yeah, it does, exactly. No, sure. That's actually the, I looked at the reference again in case I wanted to make sure that this is really what happened, but yes, sure. Okay, so this is, in a nutshell, ADS3 CFT2, like the most elementary aspects of it. Now we want to take the flat limit, meaning the limit where L goes to infinity. By the way, L is dimension full, so saying L goes to infinity doesn't make sense. You can make this all proper by introducing a dimensionless parameter, which again you call epsilon. I guess var epsilon now, because it has nothing to do with the vector field. And it's dimensionless, so you can take the limit where that guy goes to 0 if you want to, but here I'm going to be sloppy and just call it L going to infinity. That's it. So this limit is really an ultra-relativistic limit or a Carolean limit because the speed of light from the boundary point of view goes to 0. And so what we're going to do now is to take this guy, the conformal generator, and declare that we're going to expand it in powers of 1 over L. But now you have to be careful because if you write, so you have a generator epsilon, which is a function of x plus. That's your conformal generator. However, you have to keep in mind that this is this is a function now of x plus, which itself depends parametrically on the ADS radius. So actually, you have to do a double expansion. You have to take a Taylor expansion in x plus, and you have to take a 1 over L expansion in terms of the parameter here. And so when you do this expansion, we're going to assume that the expansion takes, so first we're going to assume that this guy is finite in the flat limit. And so we're going to assume it actually goes to a function epsilon, var epsilon now, of x plus, plus 1 over L times some function which I'm calling a of x plus. I don't know what that function is, but I'm saying it's here. And then I have plus 1 over L squared corrections, which I don't care about. So this is as L goes to infinity. And then you do the same, of course, for the barred guy. So you say that epsilon bar, you put the bar here, you put the bar here, because they're independent. And now you actually Taylor expand this guy. This is now a function that only depends on x plus. There's no L, so you just expand this. So this is epsilon of phi plus, so now let me make no mistake, plus u over L epsilon prime of phi plus a of phi over L plus small corrections. And now notice that everything here is a function of phi. There's no x plus anymore. And again, you can do the same thing for the barred sector, except that then you find a minus phi here, you find a minus phi here, and have a minus phi there. OK, is this clear? Because this is sort of, I guess this is one of the, it's completely elementary, but it may be one of the most subtle parts, computational parts of the talk. I guess, yes, you have a question. I'll repeat the question. It's fine, don't worry. So I'm calling so the question is, why do I call this ultra-relativistic when the speed of light goes to 0? So the short answer is because by definition, an ultra-relativistic limit is a limit where the speed of light goes to 0. And so now let me explain why this is so. The reason is because if you look at a light cone and you take the non-relativistic limit, so the Galilean limit, well, the speed of light, so what Galilean limit means, you're looking at processes that all take place at relative velocities that are extremely small compared to the speed of light, which means for all practical purposes that you can actually open your light cone and let the speed of light go to infinity. That's the non-relativistic Galilean limit. Well, then the opposite limit is the limit where everything moves at the speed of light. So that's the Carolean ultra-relativistic limit. And notice, by the way, that then your light cone is completely closed, which means nothing moves. In fact, what people normally say is that it's Carolian by reference to Lewis Carroll's book on Alice in Wonderland, where Alice runs, but while she runs, she actually stays at the same spot. That's what happens here because all light cones are closed. So that's the limit we're looking at. Thanks for the question. Blah, blah, blah. This I said, which is yes. Yes, good. So it turns out that if you want, yes, so we take these conformal generators epsilon and epsilon bar, we expand them like so. First, there's a Taylor expansion, but there's also a parametric expansion. And it turns out that if you want, so if you require that xi be finite, the vector field be finite in the limit, in the flat limit, you have to require, in fact, that epsilon of phi, var epsilon of phi, plus epsilon bar of minus phi, these guys have to be, the sum has to be equal to 0. So in other words, epsilon bar of minus phi coincide with epsilon phi. You've killed one arbitrary function. There's only one that remains. And so then when you implement this constraint, I should not have put this here. Yeah, so when you do the so it's a good question. When you do the computation, you see it, and you see it because you require, so you want to write this vector field in terms of, there's a component d over du and a component d over d phi. And you require both components to be finite. It turns out that you're going to have an infinite component. Now, I don't know which one anymore. I've done the computation a few days ago, but now I don't remember which one. But one component, you can actually do the exercise if you want. At this point, you really have all the tools needed to do it. And you can verify that if you do not impose this condition, you're going to have a term which is linear in L times d over d phi. And so that's infinite in the larger limit. So we require that not to be the case. We require that this, well, doesn't arise, which then actually sets a relation between epsilon and epsilon bar. So instead of having two independent parameters, we only have one, which is why we have only, sorry? So it's going to be the coefficient of L. Exactly. Sorry? Microphone, sorry, yes.
It's going to be the coefficient of L.
Yes, yes. So sorry, for the online people, I actually don't know if they're online. So for online people, the question was, why am I setting this constraint? And the reason is because when you write this vector field as d something times du plus something times d phi, we're going to find a component which is L times this combination. And that's infinite in the larger L limit, so you have to set this to 0 in order for the limit to be finite. So once you do this, what you find is that this vector field now, so this is really not the, well, these two are not supposed to be the same thing, but when you actually do this, when you take these guys, plug them here, implement this constraint, what you find is that these guys, so the conformal generator actually becomes alpha plus u var epsilon prime du plus epsilon d phi. And so there you've won, because now you've shown that actually your BMS vector field, up to this radial part, which is just the purely bulk part, actually emerges as a genuine flat limit from a conformal generator. Yes, by the way, I should mention, yes, sorry. What I'm calling alpha here is by definition a of phi plus a bar of minus phi over 2. So you remember I had these, in principle, unconstrained some leading components, which I didn't know what they were. Well, they're actually sort of half of a super translation. And it so happens that the super translation only sees the sum of them. The difference is sort of irrelevant. OK? Fine. So that was it. And so, yes, as I said, this is just a BMS vector field on null infinity, which we have now recovered as a limit. Is this a good point to take a break? It's been 1 hour. For me, it's fine. So I have these lines that tell me sort of when I can make a break. I have 5 pages, which is what I expected for 1 hour, so it's good. We can make a break now if people, you know, it might make sense. People don't seem too keen to take a break. I don't know. I have to read the room. Do you want to break? So tell me, do you want to break? I can, OK, I can keep going. Yes. So yes, now I want to tell you about the corresponding surface charge. So, well, how do I do this? First, let me erase this because I don't need it. So just to recap, I have first introduced BMS as a generalization of Poincaré, and we got this vector field. Then I returned to ADS3 CFT2 and said, OK, now let's take an ultra-relativistic limit. And the miracle happened, and we found BMS again. so now we can start applying this limit to other objects, such as the surface charge. So let's now ask, in this limit, so what's the limit? What's the ultra-relativistic limit of Noether charges? Well, you can just, again, you can just do the exercise, and you can find that this charge here in the flat limit, so again, I'm going to write the expression and then explain what I mean. So the limit that you find as L goes to infinity is again finite and takes the form of a function j of phi times this var epsilon of phi. So this is a super rotation charge, a super boost charge, plus a function p of phi times alpha of phi. This is now a super translation charge. And what I'm calling j and p are two functions defined as follows. So p of phi, by definition, is the limit as L goes to infinity of 1 over L t of x plus t bar of x minus. So that's really like, so that's literally the energy density of the CFT. In other words, it's the current of super translations, as you see in the charge. And what I'm calling j of phi is, by definition, the limit as L goes to infinity of t of x plus minus t bar of x minus. And then you actually have to remove a term minus up prime. So if you take this limit, you'll find that you have one term which involves this limit, which is plus up prime, plus another independent function, which you happen to call j of phi. And so that's sort of like the angular momentum density. You can call it the momentum density if you will, but here it's angular momentum because we're on a circle. And so it makes perfect sense, right? I mean, the density of angular momentum pairs in the charge with the super boost generator. The energy density pairs in the charge with the super translation generator, so perfect. Now, in terms of Fourier modes, you can rewrite this and say that you so this, I actually want to keep this. Okay. So in terms of Fourier modes, we can now define that what you call Pm. So the modes of this function P are limits as 1 over L, as L goes to 0, of Lm plus L bar minus m. And Jm is, by definition, Lm minus L bar minus m. That's really just what comes out of here. You can just take the Fourier modes of T bar, plug them there, recover these Fourier modes. And then you can plug this back into the Virasoro algebra. And so here I'm actually going to just erase the central charge. So you have two Virasoro algebras, L and L bar, which together, in terms of J and P, become, so Jj is the following bracket. So it's m minus n j m plus n plus c1 over 12 m cubed delta m plus n, 0. I jm pn equals m minus n pm plus n plus c2 over 12 m cubed delta m, 0.
Can I ask you a quick question? Sorry.
Yes.
Usually in the Virasoro algebra, the central term has m squared times m minus 1.
Yeah, I was expecting this question.
Okay. I don't know if it's important, but like...
No, sure.
This
is
is
a
what
question. So normally people present the Virasoro algebra as having a term, a central term, which is not m cubed, but m times m squared minus 1. This simply has to do with the normalization of energy. You normally, so the way, so in that normalization, which is standard, you declare that L naught acting on the vacuum gives 0. But actually, you can declare that L naught acting on the vacuum gives you the vacuum energy, whatever that is. And here, my normalization is that the vacuum energy is, I guess, minus C over 12. And when you do this, you just remove this minus 1 term. So in other words, the term linear in M in the central charge is a trivial cocycle, which you can just remove by redefining your generators. But the M cubed term is the non-trivial central extension. That's one that you really cannot remove by any redefinition. Okay, and so if you perform these definitions, whose Fourier modes are given here, plug that back into the Virasoro algebra, and then just write what happens is this algebra, I'm going to soon tell you what these central charges are, And in the bracket of p's, you find a term which is of order 1 over L squared times something, but that's 0 in the limit L going to infinity, so this actually becomes 0. So, yes?
About ADS-CFT, and we work purely in the CFT side, what does the limit L goes to infinity corresponds to? And how would we...
Oh, that's
maybe
the Carolian limit. That's really the Carolian. Actually, you said if we don't know anything about ADS-CFT, but actually I've barely even written anything about ADS. All I've written is just CFT. So in a sense, you can even think of this as a prescription that tells you how to deal with a Carolian CFT.
Scale your coordinates with some L, which is some parameter, and you...
Which is the speed of light.
It's
I'm
the
saying
speed of light.
take a CFT for which you take the Carolian limits. This is what you're going to find. I guess, well, yes. But oh, yes, and there's, so by the way, I should mention that there's an equivalent point of view, so let me just complete the answer here. So I haven't told you what these central charges are, and in fact, what you find is that C1 is actually C minus C bar, which, as I said, is non-zero only in parity breaking theories, and C2 happens to be C plus C bar over L, which is dimension full. So this is now a dimension full central charge between super boosts and super translations. And so we have actually checked this point here. We now have a central charge between super boosts and super translations. By the way, I should also mention, I forgot to check this. In 4D, super rotations are singular, but here they are smooth. So in this case, we have smooth super rotations, and so in a sense, we don't address the problem that 4D super rotations are singular, but at least we have a way to evade this problem here because super rotations are perfectly smooth and well-defined. And we have a central charge between super rotations and super translations. And just to segue into the answer to your question, actually, you can think of this as a way to address the question, how do I deal with a CFT with, which has two sectors, left and right, but the central charge goes to infinity? So I have a CFT with an infinite central charge. What's that? Answer, it's a BMS field theory. So that's another way you can think of this question. So I don't know if people online can hear. So does it matter if we take plus infinity, future infinity, or wait? Yeah. What do you mean plus or minus infinity?
Yeah, because sometimes in the CFT it's crucial if we take C going to minus infinity or to plus infinity.
No. Here it's C going to plus infinity. C and C bar both go to plus infinity. L is positive. I'm not talking about non-unitary stuff. No. This is a perfectly unitary CFT, except I'm taking the central charge to be infinite. And I'm asking what happens in the infinite central charge limit. What happens is this.
Okay, thank you.
And in fact, I would even argue that this gives you a good perturbative way to deal with CFTs at very large central charges. Instead of, we have a CFT with central charge 10,000, and you ask yourself, what should I do? Well, you can maybe start with BMS and then take small perturbations that will actually give you back the CFT. Anyway, yes, Monica, you have a question.
Sorry, so this issue about the central charge going to infinity is just because you want to keep C2 finite in the L goes to infinity limit? Or where does it come
I would say it's a corollary, really, because it's not just that I want to keep the central charges finite. I want to keep everything finite. I want my vector field to be finite. I want my functions to be finite. Everything that depends parametrically on L, I want it to be finite as L goes to infinity. And the only constraint I have to impose in order for this to be the case was this one. That's the only constraint. So in a sense, you can think of this as saying that, so what's the intuition? Epsilon is the left-moving conformal transformation. Epsilon bar is the right-moving one. So you're saying that the two cannot quite be completely independent. You're saying what I do to the left, I cannot quite do anything I want to the right. I can up only at order 1 over L. But at large L, I sort of have to do the same conformal transformation in both sectors.
But what I don't understand is what does this have to do with the central charge? So I can understand that you're taking this So I guess you're taking some very particular kinematic. I mean, in a CFT, if I just start with the CFT, I have a speed of light and I have a central charge, and those are two independent objects.
You're saying in a generic CFT, there's no relation between the central charge and the speed of light.
Because you presented this as you're taking the Carolian limit of the CFT.
Okay, that's a good point. That's a good point. It's true that in a CFT, I could imagine having a CFT which is Lorentzian, not Carolian, and still has central charge 10,000. Okay, that's true. Sure. But although I wonder if there isn't a way to to reinstate the central charge. I don't know. I would have to
what
think
I'm
harder,
saying, it looks to me, at least what I thought I had understood is that you're taking this Carolian limit of your CFT.
Yes.
And then I thought that the reason that you also want to send the central charge, the initial central charge to infinity as you take the Carolian limit is because you want some finite central extension in the JP.
I don't. I'm not asking for this to be finite. Well, sorry. I'm not asking for this to be non-zero. I am asking, so okay, that's true. Here I'm assuming, okay, that's actually true. This is an implicit assumption. I'm assuming that C and C bar scale with L as at most something times L plus order 1 corrections. Well, at least plus corrections that are small in the large L limit. That's true. That has to be, oh no, actually even more. No, I'm asking that C and C bar really scale like something times L plus something of order 1 plus something that's smaller than 1. That's true, because otherwise one of these two is going to be infinite.
Okay,
so that's okay. That's a constraint on the class of central charges I can look at. That's true.
And so the fact that you do require this finite C2, does that come from the BMS analysis in 3D?
Oh yes, yeah, absolutely. So again, I'm doing all of this because I sort of emphatically want to avoid completely the detailed asymptotic symmetry analysis, which I could have presented, but it requires tools in symplectic geometry, which I don't want to talk about. And I assume that people are much more familiar with CFT than with Bondi coordinates. So it's much easier to do it in terms of CFT.
So in order to end up with an algebra that ends up reproducing the asymptotic analysis of BMS3, which includes a finite dimensionful central charge between super boosts and super translations, then if you want to write that as a Carolian limit of the CFT, in the Carolian limit, you have additionally to send the central charge of the CFT to infinity.
You don't have to. You can have C2, which is 0. Oh, sorry. Yes, if you want C2 to be non-zero, yes, you have to send it to infinity. Absolutely. Exactly. And in fact, yes, so this is a good segue. So actually, in the gravity analysis, because you may remember that C bar were the Brown of the central charge, actually this is equal to 3 over G, which is the Planck mass. So it's quite, I mean, at this point, as I said, when I checked the point there on the right, we have a sort of neat way to see a dimension full central charge emerge, and we even have sort of a scale for it. We know that the central charge is essentially effectively the Planck mass, and it's a central charge between super boost and super translations. And so a lot of what we're going to do is actually going to be aimed at understanding the physics of that extension. Just a second, I should mention that from a mathematical perspective, this is not exotic. For example, in the Bargmann algebra, there is also a central extension, which is the mass of a particle. So having dimension full central charges is not a surprise for a mathematician, but it may be a surprise to a physicist who is used to CFT. So this is sort of like an ultra-relativistic CFT, which happens to have a dimension full central charge. Yes, you had a question.
Yeah, so in CFT, the way we generate the central extension is just a way of generating the central extension is comes from this ordering ambiguity that we talk about in.
Yes.
So can you get the central extensions here by talking about ordering ambiguity, or this is the only way of
okay, you mean like in a genuine quantum field theory
exactly.
that would have
if I write the classical
where I have
algebra
to normal order everything, I have no clue. I suspect that the answer would be yes, but I don't want to state anything, especially because at this stage it's completely classical.
Okay.
So I don't dare saying, but I'm pretty sure that if it's you see, the problem is that here the energy spectrum is going to be continuous, as opposed to a CFT spectrum, which is sort of always discrete. Of course, the gap is 1 over L in a CFT, so it's a gap that becomes smaller as the CFT becomes more Carolian, but still it's non-zero. Here it's really going to be a continuous spectrum. So it's a bit like talking about a Lorentzian QFT, where you have to deal with a continuous mass spectrum. And it's, these ordering things, I don't know how they would exactly work here. So it's a subtle issue. Actually, what people have done is to consider this as this is actually part of the conclusion, but it turns out that you get the same symmetry algebra if you look at the non-relativistic limit of a CFT, with the key difference then that P0 is actually a generator of rotations, while J0 is now the Hamiltonian. So it's physically a completely different setup, but in that case, you effectively get a CFT, sort of a chiral CFT, with some dressing by super translations. And then you have these notions of ordering, which sort of tend to produce this, for example, you can see it from OPEs and things like that. But that's a non-relativistic CFT. Here it's an ultra-relativistic one, and I don't really know how that would work. Actually, I don't think it has been done, but I'm not sure.
And I have a second question about, in a CFT, we know that the trace of the stress tensor will give you the anomaly term, like R times C,
yes.
some number.
Yes, yes.
And is it going to give me some new information on in the BMS?
No clue. No clue. Maybe, but no clue. You would have to couple the BMS invariant field theory to some curved background, presumably, and then see the anomaly. I don't know.
But if I take the large L limit on the CFT side and go to the BMS side,
I understand the question, but I really don't know. I really prefer not to say anything because I will, I'll crash. I prefer, in this case, I don't even have an intuition for what would happen. What would even be? Would you even get a well-defined? The curvature that you find in the CFT side is the 2D curvature. Which one would you get here? Would you get the Carolian curvature? But what's the Carolian curvature? Is it the curvature of the base manifold without the time, or is it just the time one? I really don't know. So, to me,
technical issues, because I can write down an equation with the trace of the stress tensor is C times R times by some number. And then if I take the L goes to infinity limit,
sure. But the L goes to infinity will affect also what you call the curvature, because the metric is hidden there. That's exactly my point. I don't know what you mean by curvature, because curvature in a Lorentzian spacetime, okay, fine. But here it's a Carolian spacetime. It doesn't even have a metric, like not an invertible metric. So how am I supposed to? I don't know how to make sense of it. I strongly suspect, I'm willing to, conjecture that it does work, but it's no more than a conjecture. I cannot claim it honestly. Okay, so please do let me know if you want to break. I mean, I have points when I can make breaks, so I can continue as long as you want. Yes.
Let me ask one more question before the break. So,
sure.
What are the limits on adding dimensionful central charges from the mathematical point of view? You've given some examples where the central extension is dimension 1, but what is possible mathematically?
You mean dimension 1 in terms of mass, like power counting?
Yep.
None, because for a mathematician, dimensions do not exist, right? A mathematician would always tell you that a dimension is just a matter of convention, so who cares? The limit here comes not from dimensions, but from cohomology in the sense of the algebra. You can always ask, if I give you a Lie algebra, I tell you, here's the Lie algebra, take it, and now tell me what are the possible central extensions. You can always compute what's called the second cohomology group of the algebra. Actually, you can do this also for the group, but let's focus on the algebra. And that cohomology group is going to tell you where you can put central extensions and what form they take. And it turns out, for example, that you can prove for the Witt algebra, so just this first line here, equivalently this one without the central extension, we can prove that the only central extension that you can add up to redefinitions is this one. And in the same way, in BMS3, so if you take this whole thing without central extensions, you can prove that the only thing you can add while preserving Jacobi identities and leaving it to the algebra is something like this. So there's no other possibility. I should mention that actually, so this is why this is sort of very powerful, because in BMS4, this is not true. Actually, in BMS4, when Glenn and Cedric found this central charge, they were very puzzled because they had done the cohomological analysis, and they had found that there is no possible central charge. And actually, other people recently have confirmed this. And so they didn't understand this, but the solution comes from the fact that here the central charge is field dependent. It's actually the asymptotic shear that plays the role of central charge. And so that completely evades the classical cohomological analysis. This is an analysis for the algebroids as opposed to the algebras, and it's completely different. So that's why you have a central charge here. Thanks, yes. Hi, online people. So there was a question about string theory, and I was saying that you can derive the ADS3 CFT2 symmetry from string theory. This is a paper by Gieven, Kutaszów-Seiberg, but I believe this has not been done in flat space. So I don't know if anyone knows how to derive BMS3 from string theory. And then you were about to jump in with a question. Yeah, microphone. But you can ask it and I repeat it, it's fine.
When string theory in three-dimensional Minkowski doesn't exist, right? You have to have the 7 dimensions, and there you may not have three-dimensional flat space. You may end up in higher dimensions.
Sure. Oh, so you're saying even
like in ADS3 S3T4, that's like the poster boy of string theory in ADS3. If you blow up this, you will land up in 6-dimensional Minkowski, not in 3-dimensional Minkowski.
Yeah, okay, I see. Oh, so you're saying that there might be an issue with the fact that the compact dimensions are actually going to contribute extra dimensions to Minkowski, so there may be a good reason why you're actually unable to do this for string theory in 3D flat space. Okay,
Possibly,
good point.
yeah.
I don't know. Good point. I remember when I was still a PhD student, and I think it was Jelle Hartong who actually tried to do this, and we talked with him at some point, but he said it was a mess. I mean, effectively, it's sort of a mess because you write things in boundary coordinates, and when you write the world string action, you find things in boundary coordinates, and they're much messier than Pfefferman-Grimm coordinates. It's much harder to do things. So it seemed at the time just like a technical issue, which maybe can be solved, but I really don't know how it can be done.
Definitely still an open question whether there can be string backgrounds with only 3 large dimensions being those of ADS3 and the rest small.
Right.
All the nice examples don't have that. We don't know if it's possible within string theory, though.
Okay.
So it could still be.
Good. Thanks for the questions. So okay, I think I've managed to keep the few things I actually want to still display. So just to recap, I have now defined BMS, baby BMS, BMS3. We all know what it is. So now I want to actually relate this to gravitational boundary data. Oh, and I did erase a charge. Bummer. I didn't. There's one thing I didn't want to erase. So remember that the charge associated with the super rotation epsilon alpha was integral d phi over 2 pi plus p of phi. This I already wrote, but it's just for future reference, I want to write it here. Okay. So okay, I can keep here all the things I actually need. Okay, so let's now ask about the relation between the BMS algebra, as I've defined it, and what I'm going to call boundary gravitons, i.e. The boundary degrees of freedom of the gravitational field in 2+1 dimensions. So again, I guess everyone knows this, and I've stressed it already, but let me still repeat. In 2+1 dimensions, there are no gravitational waves, no local degrees of freedom, so everything is topological, and in the entire dynamics of gravity is localized on the boundary. And so, in particular, you can take an asymptotically flat metric, meaning a metric of this form asymptotically plus certain corrections which I do not bother writing down, and you can ask, what's the solution of Einstein's equations? Literally, you can just say what's the general solution of Einstein's equations given these 4 laws that I've prescribed. And the solution turns out to take the following form. So you have a metric which on shell is equal to, by the way, this is now an equal sign. This is not going to be asymptotic. This is really what the metric is. So you find that it's labeled by 2 arbitrary functions, which are going to have very suggestive names, plus G of U P prime I. So you find that the most general on-shell metric in 2+1 dimensions, which is asymptotically flat in this sense, takes this form and is labeled by 2 functions. One which I call P, which is called the Bondi mass aspect. It's really the density of energy at non-infinity carried by the gravitational field. And the other one is the angular momentum aspect, for sort of obvious reasons, because as you can see, this guy comes in the du d phi term. So that's the mixed term which carries angular momentum from the point of view of the metric. And so, of course, the notation is not coincidental. I'm calling them P and J because actually the surface charge, now really the, if you consider an asymptotic Killing vector field generating a BMS transformation and evaluate it on a point which happens to be this solution, the corresponding surface charge is actually a BMS Noether charge. So it's really this guy. Or in other words, it's an ultra-relativistic CFT charge. And so the terminology is that I'm going to refer to the pair JP, so a function J and a function P. That's what I'm going to call a boundary graviton. I believe the same, well, actually the same terminology is used in ADS3 as far as I know, where the stress tensor of the CFT on the boundary, you would call that a boundary graviton. And so just some examples. So when I say examples, I want to say, I'm telling you that the most general 3D asymptotically flat matrix solving Einstein's equations takes this form. Now, which metrics are actually included in this story? Well, first of all, you better hope that Minkowski is included. And it is when you take, so Minkowski is J equals 0 and P equals minus C2 over 24. And so this is really like, you're saying that it has 0 spin, 0 angular momentum, and it has some non-zero Casimir energy, if you will, just like in CFT. Okay. Then conical deficits are also included. So now let me actually give you the formula. By the way, these are all things that you can actually verify. You can do well, this exercise is sort of trivial because you can just plug those things with E2 equals 3 over G. You can immediately verify that this is actually the Minkowski metric that I wrote earlier. But for the conical deficit, this is a genuine exercise, if you will. So suppose that it has an opening angle theta, by which I mean that you take the plane, the spatial plane, and you cut out an angle theta. So you remove this part of space, you rewrite the metric, and what you will find is that the metric takes this form. With J and P, which are constant, actually you can add spin. So this, if I want, I can add spin, some value S, but you don't have to. And P happens to be a constant given by minus C2 over 24, 1 minus theta over 2 pi, the whole thing squared. Notice, by the way, that for theta equals 0, this indeed reduces to the Minkowski metric, as it should. And for theta equals 2 pi, so if you go to the extreme limit where you close everything, this guy goes to 0. So what happens when suddenly this guy becomes positive? You obtain what are called flat space cosmologies for reasons that I will not go into. So with spin S and mass M, I'll take again J to be a constant S and P to be M minus C2 over 24. And so you can think of these flat space cosmologies as flat space analogs of BTZ black holes in ADS3. In particular, notice that they have now I should mention that M here is greater than C2 over 24. So there's a mass gap. You are, if you increase the mass, you start from Minkowski, and now you increase the mass. First, you get to conical deficits, and then once the mass becomes larger than the Planck mass, suddenly you are in a flat space cosmology. So you change the causal structure of space-time because there's now a Cauchy horizon, but I will not go into those details. Anyway, this is sort of a basic zoo of the metrics you find. Yes, there's a question.
Respond to flat space cosmology, you have horizons. Can you see that? Like
Cauchy horizons, yes. They're not event horizons, but
I
they
see.
do have horizons.
Okay.
Off the top of my head, I do not remember the Penrose diagram for them. I remember I wrote it at some point, but I don't know what it is exactly. They do have horizons, and there's a notion of temperature, there's a notion of entropy associated with those horizons, and this entropy is given by a Cardy formula, which you can derive from BMS symmetry. This has been done.
I see.
But it's a bit weird. It's not as well behaved as the ADS CFT case. It's a bit.
Thank you.
Well, I don't know. It seems a bit singular because the angular momentum is not bounded, and so there's some convergence issues. But if you sort of close your eyes and just do the computation naively, it works.
Black holes we can have only in where we have like hyperbolic metric. When
Sorry?
we can have stable black holes we can have only in the case where we have asymptotically ADS space.
Yeah, exactly. In 3D, there are no black holes in flat space.
Yeah.
Exactly. Crucial point. So, so this is just to give you a brief idea of what these metrics are. But now there's a key point which I want to write, and I'll write it here. Perfect. So, of course, these metrics are asymptotically flat. So if you take a BMS vector field and you act on one metric of this form, you're going to map it on another metric of the same form, but with different functions P and J. And so in particular, we can ask how BMS acts on boundary gravitons. And so the answer turns out to be the following. First, so just to clarify for those who maybe are not familiar with this, what I literally mean by this is that you can compute the Lie derivative of the metric, taking a metric of this form with respect to a vector field psi, which happens to be a BMS vector field. So you compute this, and you deduce the following transformation laws. You find that delta p is given by epsilon p prime plus 2 epsilon prime p minus c2 over 12 epsilon prime prime prime. And delta j is epsilon j prime plus 2 epsilon prime j minus c1 over 12 epsilon prime prime prime. And then plus alpha p prime plus 2 alpha prime p minus c2 over 12 alpha prime prime prime. And so now, okay, does the audience recognize the first equation? This is the transformation law of a CFT stress tensor. So P transforms under superboost as a CFT stress tensor, but with a dimension-full central charge C2, which makes sense because P is a density of energy, so it's also dimension-full. Perfect. Now look at the transformation law for J. The starting point is again the same. It's the transformation law of a CFT stress tensor, except now there's a dimensionless central charge C1, which is typically 0, and if it's non-zero, it means parity breaking. Now I have a question. Do you recognize this? Do you have an intuition for what it is? Because there's a there's an elementary intuition. So first, if you just look at it, it looks like a CFT transformation law, except that now your CFT parameter is somehow alpha, and the current is P, and you have the central charge C2. Okay, fine. But if you just think in terms of classical mechanics, why does this term have to be here? You knew it had to be here before you even did the computation. If you look at angular momentum and you perform a translation, you're changing the origin. So if your state has momentum, you're adding orbital angular momentum. So this is actually alpha cross P. This is just orbital angular momentum. That's it. And it happens to take this form because of the group structure and everything, but that's just what it is. From an abstract point of view, you're just recovering the fact that the angular momentum aspect receives two contributions, one which is the intrinsic one, and then another one which is the orbital angular momentum. Okay, fine. And so this, I've said everything I wanted to say. Yes, these are going to be important. Do I have space? So this I don't need. Okay, good. So apparently this line is going to be the line where I keep my equations that I'm going to keep referring to, but this I don't need anymore. So let me erase this. This I do need. Okay. So at this point, you can start asking genuinely physical questions about what BMS does to those metrics. And so one very elementary question you can ask is, if I take a metric here, say Minkowski space, and I act on it with all possible BMS transformations, what's the family of metrics I obtain? Well, I obtain what we would call an orbit of metrics. It's the orbit of Minkowski under the BMS group. And you can ask about, you can start asking questions about that orbit. For example, you would physically want the energy on that orbit to be bounded from below. Because if it's not bounded from below, it means that you can perform BMS transformations that would indefinitely, that would always lower in an arbitrary manner the energy of the state you're looking at, and that would be, physically unpleasant. And so you can address sort of a positive energy theorem, which you state and resolve just by looking at this equation here. You can just say that P transforms as a CFT stress tensor, and P is the guy that contains information about the energy, because it's the zero mode of P that actually measures the energy. So if you start from some given P and you act on it with all possible superboosts, is the energy of that guy bounded from below or not? And the answer is energy. So let me write it properly. So the only metrics whose energy is bounded from below under BMS transformation, bounded from below under BMS, are those in the orbits of, and now there are three possibilities, either Minkowski space, three possibilities. Minkowski space, zero modes, all zero modes with mass m, which is positive. So if you take this equation and let m be strictly positive or zero, the energy is bounded from below, but otherwise it isn't. And finally, or, no space, or one exceptional non-zero mode. Can you actually read what I'm writing here? Exceptional non-zero mode. When I say non-zero mode, what I mean is a metric for which the functions p and j, well, typically p in this case. So here we only care about the p piece. When I say non-zero mode, I mean a metric whose function p is not a constant. And actually, you cannot turn it into a constant by acting with superboosts. There exists no superboost that would turn this into a constant. So there is the only metrics for which energy is bounded from below when you act on them with BMS transformations are Minkowski and all the BMS transforms of Minkowski, all zero modes with positive mass and all their superboost transforms, and finally one exceptional orbit of with a non-zero, well, non-constant function p, which eventually will happen to be a massless particle. And that's it for section 1. Questions? Yes, Monica.
Yeah, so on the left-hand side, you wrote the most general solution to,
yes.
to, I guess, r mu nu equal to 0.
Yes.
So I thought this would just be generated by BMS from the vacuum, but I guess you're saying that that's not the case. So what
Strictly,
are
the answer is no, it is not the case.
So is there a classification of...
yeah.
This is the classification if I'm interested in positive energy.
This is actually one aspect of the classification, but you can perform the classification much more generally, and it's called, from a mathematical perspective, it's the classification of coadjoint orbits of the BMS group. In the same way that you would classify coadjoint orbits of Virasoro in order to classify orbits of ADS3 metrics. You see, forget flat space. Take pure ADS3 and act on it with an asymptotic symmetry. You are going to get a metric with non-zero modes, with functions t and t bar, which are non-constant, but you're not going to get any function t and t bar. You're going to get very specific functions t and t bar that are very specifically related to the ADS metric that you started from. In particular, if you happen to act on your metric with SL2R isometries, you're actually going to act trivially, right? Which is the whole point of isometries. So you can see already there that you're missing conical deficits. You cannot map ADS3 on a conical deficit by a conformal transformation.
But if I'm imagining that I'm acting with all the Virasoro symmetries or with all the BMS transformations, why can't I just start with the flat metric and end up with any of these PJ metrics?
Because you wouldn't be doing diffeomorphisms of the boundary. What you can do, I guess what you have in mind is that you want to map, in ADS3, you would want to map x plus on some number times x plus, which you can think of it as a conformal transformation, but that's not a diffeomorphism of the boundary, because a diffeomorphism of the boundary has to satisfy, well, now this is getting technical, but if you actually want to perform a diffeomorphism of the boundary, you have to satisfy the constraint that f of x plus 2 pi equals f of x plus 2 pi. This is not the case with the function f of x plus equals lambda times x plus. So strictly speaking, you're out of the Virasoro group. You're out of the group of asymptotic symmetries that you're supposed to be considering. Of course, if you allow yourself to perform such, if you will, singular transformations, then I agree. Then you can map anything on anything else. But strictly speaking, in terms of diffeomorphisms of the boundary, the only ones you can do are those that satisfy this. And in that case, you can genuinely classify orbits in ADS3 according to, well, the Virasoro action. So in other words, you have an infinite dimensional space of all possible metrics. So this box here that I'm drawing is an infinite dimensional box of all possible metrics in ADS. And then you happen to have very specific leaves, etc. And each of those leaves is actually one orbit under Virasoro asymptotic symmetries. And so you can foliate the space of metrics in this way, and you can again ask the question of boundedness of energy there, for example. And we did, in a sense.
I see. So just to rephrase what my confusion initially was, so basically I wanted to find a solution for some function f whose, say, Schwarzian derivative is a prescribed function, which would have been the stress tensor of the CFT, which is obviously single valued and so on. But if I'm understanding correctly, what you're saying is that well, of course, there will generically be a solution to that as long as I'm not imposing the periodicity condition. But with periodicity condition, actually, sometimes there's no solution, and there's a classification in terms of this.
In general, there is no solution, exactly. And in fact, you sort of even see it more easily with BMS, because when you work, it's very easy when you work with x plus and x minus in ADS to forget that they're really periodic. But when you work with phi, phi is 2 pi periodic from the start, and that never changes. And so you're forced to, come to grips with the fact that you're only allowed to do genuine diffeomorphisms, and that's how you start realizing these things. That in fact, this same picture applies to BMS, to flat space. So you have an entire infinite dimensional space set of, it's actually a vector space of all possible metrics, and then you can foliate this space in orbits of a metric under BMS transformations. And in fact, the orbit is really under the finite version of these transformations here, which happen to be the quadrant representation of BMS. So the orbits happen to be the quadrant orbits of BMS. So if you classify quadrant orbits on the mathematical group theory side, effectively you have classified all metrics on the gravity side. And then again, you can start asking physical questions such as energy. And as it happens, in fact, well, actually, oh, perfect, this is a good segue, yes. So as it happens, quadrant orbits in mathematics are closely related to what's called geometric quantization, meaning that you can start with the classical system and then quantize the system to obtain a quantum theory, and that's actually what we're now going to talk about. So no, actually no, that's not true. I'm going to talk about the quantum theory and the representations of BMS, and it so happens that these representations are in fact obtained by geometric quantization, but I'm not going to talk about geometric quantization because it goes well beyond what I want to talk about. So I am going to talk about quantum BMS, but geometric quantization will be for advanced questions. Okay, so the question is, we have 3D flat space gravity, and so how can we quantize that theory? That was our initial motivation, and so what we're going to do is well, really take ADS3 CFT, as we did, in fact, before. We're going to take ADS3 CFT2 as a sort of inspiration. And in particular, we're going to say that the Hilbert space of, say, perturbations around one particular boundary graviton equals, so that Hilbert space is actually a highest weight representation of Virasoro with some conformal weights h and h bar, and these weights are specified by the kind of boundary graviton you have in mind. And then the full Hilbert space, so the full Hilbert space of ADS3 gravity is going to be some sum over some weights of these Virasoro representations. And I want to stress that this is actually the point where I believe no one really knows how to make sense of this. There are proposals there's an old one by Maloney and Witten of how you can actually sort of in reverse compute a partition function and try to deduce what the spectrum would be, but then they found a negative spectrum, which doesn't make sense. So I would say that this aspect is very much an open question, even in ADS3, except if you start doing string theory. But you can at least, so you can forget about this aspect of the question, but you can at least ask the perturbative question of what happens when you try to quantize boundary gravitons around some particular background. And so that's going to, so the question is, what's the analog of a highest weight representation in BMS? Okay. Yes, a plan would be good here, but I have no space. Okay, so let me do it here. So the plan of what follows is as follows. So this is going to take the whole rest of the class, and so this is sort of modular in the sense that I can, if people are bored at some point after 2 hours, I can stop. But so let me tell you the plan. So first, I'm going to take the ultra-relativistic limit of Virasoro representations. And as you will see, the limit is going to be so weird that we'll have to revisit the question and ask it differently. And so this revisiting will be done by actually taking the Poincaré group as a sort of toy model. And I will just remind you, so this is not new, of course. The Poincaré representations have been well known for a long time, but they're sort of perhaps less familiar to audiences today. And so I would like to remind you of how these representations are built. And then I'm going to use this to build what I'm calling BMS particles, i.e. UE reps of the BMS group in 3D. And finally, if time allows, I'm going to talk a bit about holography in flat space, and specifically about the relation between characters of the BMS group and one-loop partition functions of gravity. Okay. Okay, so here we go. The first thing I want to do, as I said, is to take, so I'm going to say, we know how ADS3-CFT works, so ADS3-CFT2 works. So let me take a highest bit representation of Virasoro times Virasoro, take its ultra-relativistic limit, and see what comes out. And so here, so I'm assuming again that I have 2 sectors. Well, I've erased the entire Virasoro algebra, but you know what I mean. So I have 2 sectors of Virasoros, which are L's and L bars. And in particular, highest weight representation is one that satisfies these constraints. So I have a highest weight state H, which is an eigenstate of the operator L0 with eigenvalue H. And this guy is annihilated by all LKs with K, say, positive. I could include the vacuum here, but then I would have to start at K equals -1 here. Let me just be generic here. So I'm taking a generic highest weight state. Then a basis of the Hilbert space is provided by descendant states, which are L minus K1, L minus Kn acting on H. Okay, fine. Where the Ki's are all positive, of course. Okay. And so, well, how now are we supposed to take the ultra-relativistic limit of that? Well, this is why I actually kept this. If you look at this, you can now say, let me rewrite L in terms of J's and P's and L bar in terms of J's and P's. So you would say, for example, that for the UR limit, you declare that Lm is 1/2 Jm plus Lpm. And I need colors again. And for L bar, and this is not actually, now the colors are really crucial. For L bar, you have a minus here, you have minus M here, and you have minus M here. And I think that's all. Yes. And now you can just say, well, so, okay, I have my high-switch representation of Virasoro, which is of this form. I have the same kind of construction in the barred sector. Now I'm going to rewrite everything, all those conditions, in terms of J's and P's. Now, the key point is that as L goes to infinity, this guy becomes dominant with respect to this guy. So the J's become effectively irrelevant. And so if you now look at the condition that Lk gives 0 when acting on H, and L bar K gives 0 when acting on H for positive K, well, that actually means that Pm acting on H bar, if you will, gives 0 for every non-zero M. So this guy I'm going to call phi, just to save some time. But now, you know, if you had naively looked at the BMS algebra and tried to build a high-switch representation, you probably wouldn't have started from this. You would have started by something like saying Pk, you know, gives 0 for positive K, but non-zero for negative K. Well, that's actually not what happens. If you take the ultra-relativistic limit of 2 Virasoro representations, you find that Pm, or Pk, if you will, acting on phi, gives 0 for every non-zero K, positive or negative. And so the interpretation is that the highest weight state is a state at rest. Because if you act with, it has 0 momenta, except, of course, that, well, it has, okay, yes, sure. that it has some mass, because when you act with P0 on the state phi, you get H plus H bar over L phi. So this is your mass. And also it typically has some spin, because if you act with J0 on phi, you find H minus H bar times phi. So that's your spin. This is going to sound very much like Poincaré representations, and in particular, now your descendants now become states of the form JK1, blah, 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 JKN acting on phi, with K1, well, essentially these K labels can be anything you want. They can be positive or negative. They can do, you can really do anything. There's no longer any constraint of the form Ki positive. So these are really like boosted states. Or more precisely, they are infinitesimally boosted states because we're acting with a finite amount of those J's. And so, as you can see, this limit is, well, in a sense, singular, because it's very hard to see from this construction how you would actually build an interesting representation. In particular, you can actually prove that any state which is built, so if you take a state phi, and you act on it with a finite product of J's and P's, no matter what they are, and if that now transformed state has some definite energy, then its energy coincides with M. You can never, ever raise the energy by acting with a finite number of BMS generators, which is very troubling, because you started from a high-state representation of Virasoro, which now has, you know, a whole tower of states with the gap 1 over L in energy between different states. But now you're finding a representation which apparently has one single value of energy. It's very strange, and it's actually incorrect. In fact, the energy is not always the same. There's very much a set of different energies, but these energies form a continuum, and to find this continuum, we're going to have to be able to act on the state phi with finite boosts. Not infinitesimal boosts like here, but with genuinely finite boosts. And so that's what I'm going to do now. Monica, you had a question.
Yeah, about this value of P0. When you're taking L to infinity, is it supposed to go to 0, this M, or are you going to scale the H's in such a way?
Oh, no. I'm assuming that I can scale the, yes, okay, indeed. Just like for the central charges, I'm assuming that I'm scaling the H's so that this mass is genuinely non-zero. Exactly. Exactly.
And the fact that you get degenerate energies, doesn't that sound like 4-dimensional BMS?
Sorry?
The fact that you get degenerate energies whenever you act with these infinitesimal generators, isn't that what BMS is supposed to do?
No, it's no. No. So the whole, we are missing here the entire soft Hilbert space structure. So the point of BMS in 4D is that supertranslations are indeed abelian, but there's crucially an asymptotic shear, which here doesn't exist. You know, the Bondi mass aspect and the angular momentum aspect exist also in 4D, but the asymptotic shear only exists in 4 and probably higher dimensions. Here, there's no asymptotic shear. And it's actually the asymptotic shear that labels inequivalent gravitational vacua, all of which have 0 energy, but they're different. Here, that's actually not the case. Here, because we're acting with superboosts or superrotations, as you will see, finite superboosts do actually change the value of energy. And so they're really not soft in that sense. This is not, so I'm slowly getting to the third point in this checklist. I'm going to talk about unity representations of BMS and their relation to some sort of dress states. But the dressing here is actually not going to be Kulish-Fadev because Kulish-Fadev dressing emphatically has 0 energy. They're emphatically soft particles. Here, these are boundary degrees of freedom with non-zero energy. So they are not soft in that sense. So it's a very different thing. It's still, I think it's still instructive in the sense that you're going to see that there's an orbit structure that emerges and you can interpret in terms of, you know, quantized metrics, if you will. But the analogy with BMS4 is very, very delicate. You have to be very careful. Oh yeah, super rotations. Or even just Lorentz transformations. If you take a state, actually, the argument I just made here, you can do it for SL2R. Take SL2 times SL2, consider high-state representations, take the Inonu-Wigner contraction to Poincaré in 2+1, and try to build a high-state representation of Poincaré. You would find exactly the same thing. You would find a state, a high-state state of SL2 now, which has some mass, which is a state at rest. It would be annihilated by P1 and P minus 1, and the descendants would be all possible products of J1 and J minus 1 acting on your highest weight state. And you would conclude, you could prove from the structure of the semi-direct sum that all these states actually have the same energy m, meaning that if you act with a finite number of j's on the state, you cannot change the energy. The only way to change the energy instead is to do something like an exponential of some sum over m, cmgm acting on phi. Now this is a finite boost acting on a state at rest, and that guy now is going to have some non-zero energy, but then you have to work out what this means. And that requires actually a completely different language. So the analog here is really, what I'm doing is actually the analog of relativistic particles, where you act on particles at rest with Lorentz boosts and thereby increase their energy. Good. So let me do this. Wait, let me just put this here. I think I don't need the metric anymore, so I'm fine. Yes. So there's a bunch of equations now that I no longer really need. So I'm going to erase most of it. By the way, again, as last time, please let me know when, when it's, wait, is it actually 12:20? Are we like well over time already? Okay. So what I can do is, I mean, I don't have that many pages anyway. So as I said, this has a modular structure in the sense that I can end with representation and then just call it a day. So in theory, yeah, representations are done in 20 minutes. If I count that one page is 10 minutes, which is roughly correct, then that's it. Oh, this I need, but this I don't need. Okay, this I don't need. And this I will no longer need because I will no longer take any ultra-relativistic limit, but the positive energy theorem I want to keep. Okay. Yes, and so let me just write here. Okay. So what I want to do is, well, I want to change my chalk. So, as I said, if you try to look at this from the CFT perspective and take a limit, what you find is a bit strange. It's a bit, hard to make sense of. It actually does make sense, as I'm going to argue, but it's hard to see why it makes sense. And so to see why it makes sense, you have to go back 100 years and remember how Wigner found unitary reducible representations of Poincaré. And so the motivation is pretty obvious. The BMS group, which I abstractly wrote here, is an extension of Poincaré. And so it makes sense that the structure of the representations will be very similar. So again, Poincaré is Lorentz semi-direct product with translations. And the multiplication, by definition, this is going to be important, is if I take a Lorentz transformation and a translation alpha, and I multiply it, I compose it with another Lorentz transformation, another translation, I get the composition of Lorentz transformations, and the sum of translations up to this action, this here, of the first Lorentz transformation on the second translation. And so the irreducible unitary representations of this group are, by definition, relativistic particles. And so the question is, how can you classify relativistic particles? How can you find them? How can you constrain the entire Hilbert space just by starting from the knowledge of the group? So that's what I'm now going to do. And as you will see, once you've done it for Poincaré, it becomes sort of obvious what you have to do for BMS. What is non-trivial is that you actually can do it. So this I cannot erase. So the starting point, if you want to build UE reps of this group, is to say, let's consider the abelian guy. So the group of translations, its irreducible unitary representations are very easy to write because it's abelian. Actually, it's an abelian vector group. So all these UE reps take the form, so they're maps. So representation is a map from a group into the group of linear operators in a vector space. So here the map takes a translation. and maps it into a linear operator acting on the complex numbers. Because indeed, this is a abelian group, so its irreducible unitary representations are all one-dimensional. They just act as numbers times a complex number. And in fact, you map a translation alpha on a phase which you write e to the IP alpha, where P is an element of the dual space of translations. So when I write P alpha, what I really mean is you take alpha as a vector, you take P as a covector, you pair the two in a sort of scalar product, and you get a number which you write P alpha. So you just choose one momentum at will. You just choose any momentum vector that you want. For any choice of that momentum vector, you get an irreducible unitary representation of the group of translations. Fine? Fine. And by the way, it's unitary because this is a complex number with unit norm. So that's why that's where unitarity kicks in. Now, the key point is that if you now, so this was just the subgroup of translations. If now, let's assume that we have some unitary representation of the full Poincaré group. Well, then, for sure, that representation contains some representations of translations, and so we can suppose that there exists some state phi in the representation of Poincaré, in Poincaré rep. And we can assume that that state phi is such that if I act on it with a pure translation, so I take a Lorentz transformation, which is the identity, and a pure translation alpha, and I act on phi, well, I get e to the IP alpha for some momentum p. The momentum p is fixed, but this is true emphatically for all alpha. So for every translation, so I'm just, this is a very important point. I'm assuming that I have some unitary representation, which I'm calling U of the Poincaré group, and I know that that representation for sure is going to contain at least one momentum p, in the sense that there exists some state phi, such that if I act on that state phi with any translation, I just get the same state times this guy. So in other words, phi is a state with a momentum p. Some momentum at least must exist. It may be zero, but it has to exist. Okay, fine. So now, so exercise. Prove that if I do this, ei alpha times u f0 acting on phi, this turns out to equal e to the I p f inverse acting on alpha u of f comma 0 acting on phi. So this equality here, I'm saying this is an exercise because this is literally something we can just prove in 2 lines from this group operation and the assumption that U is a representation. So if you use the fact that U is a representation, you can sort of pass with this translation through here such that you act on phi. But as you do this, you pick up a factor F inverse because of this group operation. And so that then you have a translation F inverse times alpha acting on phi, which gives you this factor here. Now the key point is that we've assumed you have a state phi in which all translations are represented with a momentum p. But now we conclude that because of the group structure, we also must have a state f acting on phi, which is this one, where all translations now are represented by this. And so we conclude that for all p in the representation, there's another momentum. For any momentum p that appears, there's another momentum that appears, which is by definition f dot p, which by definition is p composed with f inverse. That's the guy that appears here. And so, conclusion, the minimal set of momenta in any unitary representation of Poincaré is an orbit of momenta, which by definition, so I'm going to call it OP, which by definition is the set of all f dot p, where p is fixed, but f is a Lorentz. And so, of course, you all knew this result secretly, but maybe you haven't phrased it in this language, right? So you know what these orbits are. They're actually hyperboloids in energy momentum space. And so if you draw energy here, well, and if you write momenta here, qi, these orbits take the form of hyperbolas with some mass here. You can also have the massless representation here, and then you also have tachyonic representations here, etc. So you know this classification in terms of, momenta that satisfy q mu equals minus m squared, where m is the mass of the particle. So this, of course, you knew. What is perhaps a little bit less well known is how to actually turn this into a representation. And so the way to go is to choose some orbit, OP, and define a Hilbert space H, which is going to be, by definition, the space of all square integrable wave functions on the orbit. So you can think of this as wave functions in momentum space, with an action, so a unitary operator U, which for every Lorentz transformation F and every translation alpha, acting on some wave function psi. So psi is a wave function here on the orbit, so it's a function of Q. I'm acting on that function with the operator U of F alpha being a Poincare transformation. U is my unitary representation. So to tell you the value of this wave function, I have to evaluate it at some momentum Q. And this, by definition, is the translation represented with the momentum Q times the wave function evaluated at F inverse dot Q. So again, the interpretation is sort of trivial. If you have a state psi which happens to be localized at some momentum P, say, or K, then if you act on it with the Lorentz boost F, you're going to translate the wave function so that it's now peaked at some boosted momentum F dot K or F dot P. Except that so there's an F inverse, because if you actually want to run this argument in detail, you find that it has to be an F inverse. And this translation part just tells you this is a translation. By the way, what I have described here for simplicity is a scalar representation. So I'm talking here about a particle with 0 spin. You can also include spin into the story, but I'm not going to do it for simplicity, because you don't need to do it if you want to talk about BMS, for example. You can also include spin in BMS, and it has interesting implications. But for simplicity, I'm putting this under the rug. So is this so far clear? Because that's what you do for Poincare. And because BMS is so close to Poincare, what we're now going to do is exactly the same thing, except we're going to apply it to BMS, to the BMS group. So do you have questions at this stage? OK, if there are no questions, then let's proceed. Actually, one thing I want to emphasize, really, you may notice that the language I'm using, starting in this point B, Poincare reps, I've used the language that is completely different from the language you would normally use to describe these high-stretch representations. I haven't talked about the algebra. I haven't talked about modes. This is, in a sense, the whole lesson of the story. If you want to talk about BMS symmetry, at least in 3D, you really have to control the group. You have to deal with the fact that you have to know what finite transformations do, and that requires dealing with this kind of language. So I know that it's a bit, the reason I reviewed it here, even though it's, it's old news, 100-year-old news, but I reviewed it here because I don't know how standard it is. I mean, at least when I was a master student, we sort of learned Poincare representations, but it wasn't, we didn't prove that it was exhaustive. We didn't prove that it was the exact classification. We didn't really talk about Wigner rotations, which are important for spin. So I don't know how familiar the audience is with these things, but I wanted to review them because, yes, I think they are nowadays a bit less standard than maybe other aspects. OK, so now let's apply this to BMS, and then probably we'll take a break. So I'm calling these representations, of course, BMS particles, because by analogy with Poincare, I want to think of them as some notion of particles. So we want to really do the same thing for Poincare. In other words, we want to make sense of this sort of construction where Q is some momentum on some momentum orbit OP. So we have to find the notion of orbits of momenta. Orbits of momenta under Lorentz, if you will. But of course, in this case, what we call momenta are really mass aspects. So these are now functions p of phi. And so recall that p of phi is dual to supertranslation. So it's really, in this sense, I introduced p here as something that's dual to translations. So here we have supertranslations. So their duals are Bondi mass aspects. Perfect. And then the Lorentz group now gets extended into superboosts. So each element of the Lorentz group, if you will, now becomes a diffeomorphism of a celestial circle. So it's some map f of phi. And so in particular, when you look at the definition here of the orbits, I've told you that the orbit of P is by definition the set of all boosted momenta that you can reach by acting on P with Lorentz transformations. So the question is, how do superboosts act on Bondi mass aspects? Well, effectively, the answer is already written here. Recall that I wrote to you how Bondi mass aspects transform under infinitesimal superboosts. So now you just have to integrate this into a finite transformation law. And what you find is actually a very well-known CFT transformation law, which is that f dot p is, well, this is not a definition. This is equal to f inverse prime squared, p composed with f inverse, minus c2 over 12, Schwarzen derivative of f. So this is the Schwarzen derivative of f. If you don't know it, don't worry too much. I'm never going to use it explicitly, but if you want to look it up, look it up. Okay, if you want, I can write it down if you insist, but you don't really need it. In any case, then the, the orbit that we need, OP, is the set of all possible. So we choose some function p of phi at random. We just choose it. And then we act on that function with all possible superboosts and thereby build this orbit. So when I started my PhD, that was sort of the question. What is this orbit? We knew that we had to deal with induced representations. They're called induced representations. We knew we had to deal with them, but we didn't know what the orbits are. And it turns out that they're actually very simple. They're called coadjoint orbits. Well, sorry, it's not true that they're simple. They're actually quite pretty, I would say. I mean, the construction goes back all the way to well before BMS. It goes back to the 80s when people were looking at these CFT transformation laws and trying to classify these orbits. So they have a very neat and very well-known structure. But the point is that the structure is known, and the structure is that of so-called coadjoint orbits of the Virasoro group. And so you can, I was very lucky when I started my PhD and I Googled coadjoint orbit of the Virasoro group, and the first paper that came out was a paper by Witten, which was really beautifully written. And so, I just read that one and learned a bit about coadjoint orbits, and it was very good, it was very easy for a PhD student to start. So I want to stress that when you do this in BMS, you start getting results that are very similar to what you normally have in Poincaré. So how shall I proceed? So first I'm going to try to give you a characterization of these orbits. Then I'm going to tell you how these representations look like and how you can think of them intuitively. And finally, I'm going to argue that actually these orbits and these representations coincide with the ultra-relativistic limit of Virasoro representations that I wrote earlier on. So the example here, yes. So let me give you an example. If you take the momentum p, the supermomentum p of phi, which is a function of m, if you declare now that it's m minus c2 over 24, which now is a constant, that is, well, the orbit, that is the momentum of a particle at rest, because the only non-zero modes that you've switched on are the zero mode. All other modes are zero. And so the orbit of that guy, the orbit of that momentum, is the orbit under super rotations, under super boosts of one particle at rest. But now the non-trivial part is actually going the other way. Namely, and this is actually a question that you were asking about Casimir's. So if you go, you can go the other way. You can say that conversely, suppose that I give you some function q of phi, and I tell you this function is the Bondi mass aspect of some particle. what's the mass of the particle? Well, there turns out to be an answer which comes from this classification of zero coordinate orbits, and I'm not going to prove where this comes from, but it exists. The mass is, and so this I'm just writing because, well, I like the formula. I will not read it later, but I like it. I just want to make it, to stress that this is, in a sense, explicit. So the mass turns out to be C2/24 times 1 plus 1 over pi squared r cosh squared of 1/2 trace path ordered exponential integral d phi matrix 0 xp of phi over C2 1 0. Now matrix and now maybe I can add some parentheses just to make it nicer. Okay, so if we can compute this, oh, sorry, Q of phi, of course. I gave you Q, and I ask you what's the mass? Well, take Q, plug it into this SL2R matrix, compute the path-ordered exponential, which is now a SL2R group matrix, compute the trace of that matrix, that gives you the mass. Well, and then take the R cosh of that guy, but essentially that gives you the mass. So you can do this, and in fact, you can sort of perturbatively prove that this reduces to the standard. So this is really an analog of the expression Q mu equals minus m squared in Poincaré. This is sort of a generalization of that, but it's much more complicated, of course, because here we're dealing with functions on the circle. In any case, you can do this. Notice in particular, although this I haven't actually stressed, that here you can take the momentum to be 0, which means that you're taking the bonding aspect of pure Minkowski space, and yet the representation is non-trivial because the orbit of Minkowski space under superboosts is non-trivial. So this is very much the analog of the vacuum representation in Poincaré. If you take the vacuum and you act on it with all possible zero-zero generators, you're going to get a non-trivial representation. Are there any questions? I feel like the audience is reaching the point where hunger starts to be felt, and there are fewer questions, and also this is one of the hardest parts of the talk. So shall I keep, I have literally 1 page to finish representations, and then if people are interested in the afternoon, I can say a few words about characters, but it's really if people are, I don't want to force anything. So how do you guys feel about this? Shall I continue, or do we take a break? I finished representations, good.
Sorry, I have a quick question.
Ah, yes, hello, person from the internet, yes.
So right now here, what you call the vacuum is actually a whole orbit. So it's like a vacuum orbit, or is there like a vacuum and then you act the operators and then the orbit forms like a module?
Yeah. So exactly. So when I say the vacuum, I mean, if you will, the state, the wave function, which is localized at the momentum that happens to be a constant, and that constant happens to be minus C2/24. That's the vacuum state. But then the point is that by acting on this vacuum state with all possible superboosts, you generate a Hilbert space of states, which is like the vacuum module of BMS.
But this is different from what you call like the vacuum orbit.
Yeah. So the vacuum orbit is, so the vacuum module of BMS is a space of wave functions over an orbit, and the orbit itself is what I would call the vacuum orbit in this case. So the vacuum orbit, in a sense, is the classical object, and the vacuum module is the Hilbert space built on top of that. Notice, however, that there is actually a bijection between the orbit and a basis of the module, because you can, just like in Poincaré representations, you can take states that have definite momentum, and so a basis of your Hilbert space is given by states that have definite momenta on different points of the orbit. Well, here it's the same. You can take a basis of states that have definite bonding mass aspects, and the set of all states with definite bonding mass aspects over an orbit gives you a basis of the Hilbert space, of the module. So in that sense, there's really a bijection between a basis of the module and the orbit itself.
I see. Thank you.
Thanks for the question. Yeah, I wasn't sure if this was clear enough as an answer, but I hope it works. Okay. Yes, so I've talked about this. This I don't need now anymore. So there are essentially two last points I want to address, and then indeed, let's go for lunch. So the first point is, well, what's the Hilbert space of a BMS representation in this sense? Well, the Hilbert space is just an L2 space of wave functions over a momentum orbit. I stress, of course, that now this orbit is infinite dimensional, so this is actually a space of wave functionals, if you will, but provided you're happy to work with path integral measures, this is still fine, because I'm saying path integral measures because now the scalar product between two wave functions is actually a functional integral over a quadrant orbit of the Virasoro group, but hopefully that's okay. And so in particular, the action of a BMS transformation, which is a superboost F and a supertranslation alpha on any wave function, is just given by this expression here. So the same formula applies exactly to BMS. And so congratulations, you have now built unitary irreducible representations of BMS, exactly. In particular, notice that now the energy spectrum is very much not frozen to just one value. In fact, you can see now that you really have, just like in Poincare representations where you have these orbits here, you have these orbits here which have they start from some lowest energy and then they continuously increase energy. Well, here it's the same. But you can ask, in fact, which are the orbits on which energy is bounded from below, and that actually brings you back to the positive energy theorem. So the positive energy theorem now tells you, it was a classical statement on energy, but now it becomes a quantum statement on the Hilbert space of BMS particles that you want to admit. And what this tells you is that the BMS particles whose energy is bounded from below under all superboosts are either pure Minkowski space plus boundary gravitons, or massive particle plus boundary gravitons, or the third option, which was this one, the non-zero mode, which happens to be, in fact, it happens to have m equals 0 here, so it's actually a massless particle. You can verify that this last exceptional possibility is one kind of massless particle you can have which has positive energy. There are other kinds of massless particles, but they have negative, well, they have unbounded energy in general, so they are, in that sense, physically inadmissible. The interpretation of this wave, so say you have a wave function psi here. So how should you think of it? Well, first, you can just think, interpretation. Well, first, you can obviously think of this as a particle in the Poincare sense, because in fact, it's really just like a representation of Poincare, but it is dressed with quantized boundary gravitons. And this is actually the point where we are starting to establish a link with one of the points one of the questions I stated here in my checklist, so I'll do this in white. We're starting to have a hint of the fact that if you have an infinite dimensional BMS group and you run an argument a la Wigner for its representations, you can start getting something that looks like a dressed state. I stress, however, what I mentioned at some point, so I think it was Monica who was asking, I stress, however, that these states, these boundary gravitons have non-zero energy. So they are not soft in this sense. So this is not Fadeev-Coolidge dressing. This is a different, even the word dressed is not standard, it's just that I like to use it. But I like to use it for a very good reason, because it's really what's happening from a Hilbert space perspective. You're really saying that you extend the Hilbert space of a particle in such a way that you have more directions in which your wave function can leak, if you will. And so that leaking is, in a sense, the dressing. Another interpretation you can have is that psi, so you can think of your orbit as an infinite dimensional manifold. So actually, let me make the drawing here. Yes, you can think of this orbit as a sort of infinite dimensional manifold. Actually, if you sort of set the zero mode direction here, Q naught, and then here horizontally, you put all QMs with non-zero M. So this is an infinite dimensional manifold, and let me suppose here that I have bounded energy from below, so that the orbit really looks like this. You can sort of think of it as an infinite dimensional hyperboloid. And so every point on that metric corresponds to some choice of the Bondi mass aspect. So when you have a wave function on that orbit, the wave function, you can think of it sort of like a Gaussian, which is localized roughly around this point here. Well, in that sense, this Gaussian wave function is sort of like a fuzzy metric. And I stress here that this is nothing, this is not a computational statement. This is not a statement on like mathematics. This is just a statement on how I personally think one can interpret this. And if you have other proposals, I'm very happy to hear them. I'm just telling you that, I'm telling you this because I want to put some meat on this mathematical construction I've given you. You have the mathematical construction, but it's still important to understand physically what we're talking about. And physically, we're talking about particles dressed with boundary gravitons, or equivalently about, in a sense, a Hilbert space of metrics which deviates slightly from a classical metric. There are small fluctuations around them, and in particular, there's sort of a spread both in terms of angular momentum aspect and in terms of Bondi mass aspect. Okay, so that was the check, the third check that I wanted to make here. And so finally, let me actually go full circle and relate these representations. So I'm actually going to do this here. So I would like to relate those representations to the Virasoro representations I talked about earlier. Recall that in those representations, we found that we had this condition that all, wait, no, if I can erase. So in Virasoro representation, we found this, in the limit, we found this condition that Pm acting on the state phi was giving 0 for all non-zero m. So can you now see in terms of the orbit what this means? It just means that the state phi is a state with definite momentum, but the momentum happens to be here. So this is actually an eigenstate of momenta of the entire momentum operator, and it happens to have 0 components along all the non-zero m's, but it has some definite energy, which happened to be its mass. So in other words, as I said, even earlier when I was taking the limit, phi is actually a state at rest. So you can think of it as a delta function, a wave function, localized here sharply at this point. And then if I act on that wave function with some superboost, I map it on another wave function which has some higher energy and which is located here, which has some different, some different Bondi mass aspect. And so you can really think of this as a sort of high energy limit of Virasoro high-state representations. In particular, notice now that the energy spectrum is emphatically continuous because the gap 1 over L has gone to 0. So at this point, we actually have a full picture of the quantization of BMS symmetry in the sense of irreducible unitary representations. We know how to classify them. They're classified by orbits and spin. We know how to relate them to unitary representations of Virasoro because they're they're Carolean limits of those representations. And so we have a full picture, I think, at this stage of the analog of high-state representations from the BMS perspective. And so that, I think, now is my end point because the next step is a bit, goes a bit beyond this. So yeah, thanks.
Thank you, Blagoje, for the nice lecture. Questions?
One quick one. Is it easy to see why the conical deficit metric and the flat space cosmology does not make it in this positive energy theorem?
Sorry, is there an easy way
sorry.
to see what?
So in your positive energy theorem, you're saying that the metrics that are allowed is the Minkowski and then particle-like metrics,
but
right?
Conical deficits are particle-like, right?
Ah, they are included. Okay.
Yeah.
Ah, sorry.
Provided they have positive mass. Actually,
I see.
Conical deficits and flat space cosmologies are included because they have positive mass.
I see.
Conical excesses are excluded.
I see.
That's the difference between the two.
Okay. Thank you.
More questions? I had a question about this special massless particle.
Yes.
So what is special about it?
What is special about it is that it's a non-zero mode. So there exists no superboost that will change its Bondi mass aspect into a constant. So in other words, if you want to write its metric, there's no way you can find, by using BMS transformations, any transformation such that the metric takes a simple form, at least in Bondi gauge. And so if you actually want to write the orbit representative, it's some complicated combination of cosine squared and sine squared of things. You can write it. It's known what it is, but it's a bit complicated. And it's very nice because, in a sense, it explains, you can think of it as a way of BMS to accommodating the possibility that massless particles exist. From this perspective, it's really representation theory telling you that in a world where only positive energy is allowed, you can have massive particles, but you can still have one kind of massless particles as well. But of course, the massless particles have no mass, and if they have no spin, there's no label that distinguishes any massless particle from any other. So there's one kind of massless particle, whereas there's a whole continuum of massive particles. And I mean, even from the CFT perspective, this is sort of an unknown actor, right? Because this is an orbit of Virasoro, which you can try to quantize, but whose quantization doesn't give a high-speed representation of Virasoro. And I think it hasn't been done.
I see. I was trying to, is it possible to relate this to the stuff that Andrea discussed for 4 dimensions, where they're considering scattering of, say, massless particles and looking at BMS symmetry? So is this some massless particle that you could actually scatter and have BMS as?
Good point. Good point.
Like, do you have an action representation for this thing? And that.
What do you mean by actual representation?
Action.
Action. What action?
I mean, can I represent this as a quantum field?
Really?
Yeah, as a quantum field that has some Lagrangian.
The short answer is no. The longer answer is I think it's almost certainly doable if you take a massless particle or a massless field. Like if you take a massless, say a massless scalar in 2 + 1 dimensions, and you quantize that, the particles are going to, particles plus boundary gravitons are going to satisfy this. So presumably you could do some sort of scattering. I hadn't thought of that, but that's true. You could try. But it would be, again, it would be emphatically different from what happens in 3 + 1 dimensions because there are no genuinely soft gravitons. Here we are really working with superrotations which change energy. So it's different from what's normally done in celestial CFT, but there could be links, especially regarding superrotations. So I don't know. It's actually a good point.
Yeah, a related question, but maybe the other way, about BMS4 and Carolian limit. What is
BMS4 and?
Carolian limits, understanding.
Yes. So to my knowledge, the way to think of BMS4 as a Carolian limit of something is to ask Jeffrey Compere and Romain Luzziconi and Adrien Fiorucci, because they have this proposal that they call, I think, lambda BMS, which is an infinite dimensional symmetry algebroid in ADS space built in boundary coordinates such that if you take the Carolian limit, you actually get BMS. So this is what the little that I know, and I presume it's doable that way, but I don't know the details of this.
But they have like they start with leaky ADS boundary conditions,
yes.
right? And then
they have to choose. Yeah, exactly. So,
which is very different
because they
from
want
here.
to describe news in the end, right? So they have to make something leak out of it. So it's the only way to keep news is to do this. Sure. So it's in that sense, it's not standard ADS CFT, right? Because you wouldn't. So.
More questions? Okay, if not, let's thank Blagoje again.
Thanks.